Yes,
Can
we
you
can see
see?
it. We can see it, Professor. Thank you.
So should I maybe put it in a full screen mode if I'm able? Is this better? Okay.
Yeah, that's perfect, Professor. Thank you very much. Okay. Good morning to everyone. Good afternoon. Thank you for joining us today. We are beginning today's conference with Professor Elena Cordero presentation from Universidad degli Studi di Torino in Italy, which is titled Time Frequency Analysis of Propagators for Evolution Equations. Thank you very much, Professor, for accepting our invitation. The time is yours. Please feel free to do as you wish.
Okay, thank you very much for this kind invitation and thank you very much for attending my talk. I will present results obtained in collaboration with Gianluca Giacchi, who was my former PhD student and now he has a postdoc position at the Università della Svizzera Italiana, and my former advisor, Professor Luigi Rodino, also from the Università di Torino. Let me give you a brief outline of my talk. I will introduce with the motivation study, the propagators of partial differential equations and their sparsity property. And let me say that in this talk, I will focus mainly on historical contributions. So the history of the problem of representing propagators by means of matrices which help numerical applications. So we will see curveless, shearless representations of propagators which can be represented as Fourier integral operators of Ormander type, then Schrödinger type propagators where in this case we use Gabor type representations. Then I will recall the pioneer work by Grökening concerning Gabor representation of pseudo-differential operators and the further generalizations. And build on these results, I will also present new results concerning the Gabor matrix of propagators. And as applications, we will see as examples the complex heat propagator and the wave propagator. So we will compute explicitly the Gabor matrix for such propagators. So let me show you the object of our study. We will use time frequency analysis to study the propagators for Cauchy problems of partial differential equation having propagator P as defined here, so constant coefficient operators. And we are interested in the structure of the related matrix representation. I also studied the Wigner kernel, but I'm not going to present this part in the talk. And so we will focus only on the Gabor or general matrix representation of these propagators and the sparsity of the matrix, which yields to fast algorithms. The typical examples are Schrödinger type equations, and as I said, the complex heat equation and the wave equation. So time frequency analysis provides phase space tools well adapted to these kind of propagators. The basic example is the Cauchy problem for the free Schrödinger equation, where the solution can be explicitly written in this form. This propagator can be seen as a Fourier integral operator having symbol constantly equal to 1 and the phase here phi t, which is this quadratic form. More generally, one can replace the Laplacian of the free Schrödinger equation by a Weil quantization of a quadratic form on the phase space. But let me come now to present the sequences which allow us to translate the action of an operator with the action into the action of an infinity matrix, the Gabor matrix. So we fix a window function G in L2 over T. Now we consider here for simplicity only lattice, which is a rectangular lattice, and we define by pi lambda of G, the so-called time frequency shift of G, the composition of the modulation with respect to beta n, and the translation with respect to alpha m of the window G, as I've written here. So the sequence of time frequency shifts is called the Gabor frame for L2 over D if it is a frame for L2, meaning that if there exist two positive constants, A and B, such that the inequalities in the frame are satisfied. If we have a frame, then we can also find another frame called dual frame, pi lambda gamma, the so-called dual window, such that any function f in L2 can be represented by this formula here, which is similar to basis representation, but let me underline that in general a frame is not a basis, okay? And we have a convergence in the norm of L2. So using this representation on F, putting this kind of representation and taking any operator T continuous and linear, one can end up to this nice representation of TF as the action of a matrix with entries I have represented in the red, okay? So the entries of the so-called Gabor matrix are simply the inner product of the action of the operator T on the time frequency shift pi lambda G, inner product with the other time frequency shift pi mu of G. The decay sparsity of the Gabor matrix yields compressed representations of the related operator and an almost diagonal structure, which is very nice for numerical simulations. Let me now recall the definition of one of the most popular time frequency representations, which is the short time Fourier transform. So fix a window G in the Schwarz class, non-zero, the short time Fourier transform of a function phi, a signal in L2 for instance, with respect to G is given by this integral. So roughly speaking, if one wants to know the frequency distribution of a signal f in a neighborhood of the instant time x, what one can do is simply multiply the signal f by the shift in X of a window G localized in a neighborhood of the origin and equal to 1 in a neighborhood of the origin, so that the product gives simply a modified signal and which reproduces exactly f in a neighborhood of x. And so taking the Fourier transform, we get the frequency distribution of f near the time x. So this is, roughly speaking, the meaning of the short-time Fourier transform. Using the short-time Fourier transform, one can define the so-called modulation spaces introduced by Feitinger in 1983. In particular, here we are interested in the modulation space M infinity 1, also known as the Sjöstrand class. In fact, Grökeny proved that the two spaces are the same, which is the space of symbols for which, when you take the short-time Fourier transform and take the supremum with respect to the time variable z, and then the L1 norm with respect to the frequency variable zeta, this must be fine. Using this space, Grökeny proved a very nice almost diagonalization for pseudo-differential operators. I recalled in the first line the von-Nirenberg form of a pseudo-differential operator, but the result holds for any type of quantization, so also for the Weil operator or any other tau operator, for instance. Precisely, if we have a Gabor frame for L2 over D, the following conditions are equivalent. The symbol sigma is in the modulation space M infinity 1, or there exists a sequence H in little l1 of the lattice lambda, such that the modulus of the entry of the Gabor matrix is controlled by this sequence evaluated at mu minus lambda. This means that outside the diagonal, and especially when we are going to infinity, we have an L1 decay of diagonal decay of the Gabor matrix of our pseudo-differential operator. Okay, let me now come to other matrix representation. Let me recall the results for solution to strictly hyperbolic problems represented by Fourier integral operators of type 1 with over Manders type, meaning that the phase phi is in C infinity over d times Rd minus 0, real valued, and positively homogeneous of degree 1 in the frequency variable eta. Moreover, the symbol sigma is smooth and belongs to the Ormander class S010, meaning that when you take the derivatives with respect to eta, you see that you gain in decay. You see the decay, the polynomial decay on the right-hand side. Moreover, the symbol sigma is compactly supported in the x variable. An example is the variable coefficient wave equation, which I've recalled here. Okay, for this kind of propagators, the best results we have are the one due to Candé de Manet in 2007 and the same year by Guo Labate. The Candé de Manet used frames or curvelets, meaning that instead of considering only like the Gabor case modulation and translation, they used rotation, dilation, and translations. And shearlets, for the shearlets, Guo and Abate used shearlets, they used these other frames obtained using again dilation and translation, but instead of rotation, they use shearing. Let me underline that this result holds true only in dimension d equal to 2. And in this case, we have that the related matrix representation, the entries, are controlled by omega, which omega is a pseudomatrix of mu and h mu prime, where h is an index mapping associated with the canonical transformation of the phase phi of the propagator T, and you see that we have this power, negative power, to the power n for every n. This means that they got a super polynomial of diagonal decay. And from this, we will see later, the sparsity of the curlet or shearlet representation of these operators. So curvelet and shearlet frames are effective in dealing with this kind of operators. Let me now come to another type of Fourier integral operator, the one arising as a solution, modeling the solution of Schrödinger type propagators. In this case, the phase function phi is smooth, real valued, and such that it has all the second order and higher derivatives bounded. Moreover, the symbol sigma is in the non-standard or Mander class S000, meaning that in this case we have all derivatives bounded. The phase phi generates a canonical transformation of the phase space chi obtained simply by solving this system, and the result I obtained in collaboration with Fabio Nicola and Luigi Rodino in 2009 is that the Gabor matrix of a Fourier integral operator as above satisfies this estimate, is controlled by our polynomial weight evaluated at mu minus chi lambda. Again, n for every power n in n. So, Gabor frames provide an almost diagonal matrix representation of our propagator T. And this yields again to the sparsity of the related Gabor matrix. Let me underline that in this case, sigma is in the non-standard or Mander class as 0, 0, 0. What about representing hyperbolic PDEs by Gabor frames? Let me underline that this estimate in 2 is easier than the ones obtained by Candé, Labat, and collaborators. Let me underline that here we have a drawback. In fact, Gabor frames do not provide an almost diagonal matrix representation for instance, for the propagator of a variable coefficient wave equation, which I have recalled here, this Cauchy problem. So, whereas, let me underline that curvelets and shearlets, as we saw before, do the job. So we decided to limit the study to Gabor representation of solution to PDEs with constant coefficients. The advantages with respect to curved or shearless frames, we can treat hyperbolic equation not necessarily strictly hyperbolic of any order and dimension, Our class of equations includes parabolic equations, and we will see that the Gabor matrix of diagonal decay displays a super exponential decay. Example, let me recall the Cauchy problem for the constant coefficient wave equation, which solution can be written as sum of this multiplier t sub t and the derivative of the same multiplier. So we will see that what really matters in this study is to handle and study multipliers instead of Fourier integral operators. So if we consider a Gabor frame with the Gaussian window, for instance, this is an example we can take as lattice, the one ZD times 1/2 ZD, then the Gabor matrix of the wave propagator satisfies this Gaussian-like decay with the constant c sub t and epsilon t depending, of course, on the time variable t. So with respect to the approach by Ormander's FIOs, we study pseudo-differential operators rather than Fourier integrals operators, where the eta-dependent phase functions are here absorbed into the symbol sigma t of eta. Okay, so let me first of all come to the extension of the original result by Grökenik for a more general setting of pseudo-differential operators. Precisely here, we are interested in pseudo-differential operators with a smooth symbol satisfying the estimate 3, so the derivatives of the symbol satisfy this estimate. Let me underline that if the power mu is strictly less than 1, sigma is an ultra-analytic symbol. When mu is equal to 1 is analytic, and Gevrey if mu is bigger than 1. The estimate 3 is satisfied by symbols of a large class of evolution operators with constant coefficients with mu strictly less than 1. In particular, the wave equation satisfies the estimate for mu equal to 0. Let me also recall the class, the Gelfand-Shilo space, Gelfand-Shilo class. Take a function f in the Schwarz class. It belongs to the Gelfand-Shilo space as mu nu, with mu plus nu greater or equal than 1 if there exists a positive epsilon such that the derivatives of f satisfy this estimate. You see that the index mu controls the regularity of the function and nu the decay. So the result we have in terms of the characterization of the Gabor matrix of a pseudo-differential operator in terms of the symbol is the following. Consider a mu greater or equal than 1/2, a window G in the Gelfand-Shilo space as mu mu, then the following conditions are equivalent for a smooth symbol. Sigma satisfy this estimate, or the continuous Gabor matrix satisfy for a suitable epsilon, positive epsilon, this exponential type decay. Number 4. Let me underline that the Gevrey case for mu bigger than 1 was already proved in another paper by Grökener and Resnowski, whereas mu equal to 1 can be easily inferred from their work. So what is really mu is the case mu strictly less than 1. Let me also underline that we first got the result for the continuous Gabor matrix, but from them it is easy to come to the discrete, the real Gabor matrix of the pseudo-differential operator. In fact, if we consider a Gabor frame with window G in S mu mu over D, for instance, take the Gaussian, which is in S 1/2 1/2, then the continuous Gabor matrix decay is equivalent to this discrete version number displayed in the estimate number 5. Now let me come to define explicitly the sparsity of the matrix. So if the estimate 5 holds, then the Gabor matrix is sparse. What does this mean? If you consider any A, B to be any column or row of the Gabor matrix, and with these absolute values, A sub n be the n largest entry of the sequence A, then this nth largest entry satisfy this estimate is controlled by a constant times this exponential to the power minus epsilon times n elevated, to the power 1 over 2d, d being the dimension, and mu being exactly the index mu we have in the decay of the Gabor matrix. Let me underline that in comparison with the curved and shearlet matrix, we have a better decay because their nth largest entry satisfies only a super polynomial decay, whereas here we have more, we have exponential type decay. Okay. So let me come now to application to evolution equations. So we consider our partial differential operator and the related Cauchy problem with data in the Schwarz class. It is well known that the forward Cauchy problem is well posed in the Schwarz class if and only if the forward Hadamard-Petrovsky condition is satisfied, meaning that there exists a positive constant C such that taken tau eta in C times Rd such that pi, which is the related symbol of the operator, pi evaluated at I tau eta equal to 0, implies that the imaginary part of tau is greater or equal than minus C. The solution then can be represented as a linear combination of derivatives of the fundamental solution of P, our E, convolved with the initial datum and the derivatives of the initial datum. So since this fundamental solution can be seen as the inverse of our sigma, where sigma is the unique solution of this equation, where delta is the standard Dirac delta, it is enough to reduce the study of the Cauchy problem we have seen above to the properties, and so the study of the related Fourier multipliers, sigma, with symbol our sigma, which gives then the fundamental solution. Examples. we can consider the Way operator, the Klein-Gordon operator, or the Lit operator. Now we consider a stronger condition, stronger than the Hadamard-Petrovsky condition. In fact, we assume that not only there exists a positive constant C, but also R greater or equal than 1, such that given tau zeta and C times this time CD, such that pi of I tau zeta equal to 0, this implies that the imaginary part of tau is not only greater or equal than minus C as above, but we have C times 1 plus the absolute value of the imaginary part of zeta to the power r greater or equal than 1. So we have this stronger condition, which implies, of course, the Hadamard-Petrovsky condition. Under this stronger Hadamard-Petrovsky condition, the symbol of the multiplier of our operator satisfies this estimate. With mu, the power mu related to the R, we have in the stronger Hadamard-Petrovsky's condition as follows. Mu is exactly equal to 1 minus 1 over R. Since R is greater or equal than 1, then you see that our mu is strictly less than 1. So we are in the ultra-analytic case. So combining this with the almost diagonalization result we have seen above, so under this stronger Hadamard-Petrovsky condition, if we take a window G in the Gelfand-Shiloh space S SS, with S being the maximum between 1/2 and 1 minus 1 over R, then the continuous Gabor matrix of our multiplier satisfies this exponential decay, super exponential decay, where epsilon depends on the time and also the constant C. Let me underline that epsilon and C are uniform if T lies in bounded subsets of the positive real line. And since S is strictly less than 1, in this exponential, we get a super exponential decay of the Gabor matrix. Examples. Consider an operator which is hyperbolic with respect to t, then the stronger Hadamard-Petrovsky condition is satisfied with r equal to 1. So if we fix a window function g in the Gelfand-Shiloh class as 1/2, for instance the Gaussian, as I said before, then we have this off diagonal decay of the Gabor matrix controlled by a Gaussian, so a very fast off diagonal decay. We can also consider the it operator and its generalization simply by considering minus delta to the power k for any k positive integer. In this case, the SHP condition is satisfied with r equal to 2k, and so for s equal to 1 minus 1 over 2k, g in the Gelfand-Shiloh space SSS, we have that the Gabor matrix satisfy this off exponential decay for some positive epsilon. Now, let me come to the new results obtained only last year in collaboration with Gianluca and Luigi. In this case, we consider the symbol sigma belonging, consider multiplier with the symbol sigma belonging to the Gelfand-Shilov class as mu. For mu greater or equal than 0, mu greater or equal than 1/2. Then we consider window G in the Gelfand-Shilov class SSS with S the maximum between this mu and 1/2. When mu is equal to infinity, we come back to the assumption of the symbol we have seen before, and we do not gain anything concerning the decay of the Gabor matrix. In the first frame, we have exactly the exponential type decay we have seen before. The novelty here is in the case nu finite. In this case, if we split the variables z in x, psi, so we differ, x is the time, psi is the frequency variable, and w in y eta, the same, you see that in this case, the entry of the Gabor matrix satisfies a better estimate, because nothing better we don't gain in the time decay, but we gain in the frequency. The red governs the frequency decay, the red exponential, and you see that we have an exponentially accurate localization in frequency. Now, let me come to examples of application of this general theory. For example, consider the Cauchy problem for the complex heat propagator. In fact, we allow gamma to be a complex number with real part alpha greater or equal than 0. In this case, the solution can be explicitly written as this Fourier multiplier, and the symbol sigma for every time is in the Gelfand-Shilov, positive of course, is in the Gelfand-Shilov space as 1/2. 1/2 is a Gaussian. In this case, thanks to the result above, we have that the entry of the Gabor matrix is controlled by these two Gaussian. So we have this nice Gaussian decay in the frequency, and then the same Gaussian of diagonal decay in the time variable. Of course, the theory we have in general does not give further information concerning the constant c and the exponent epsilon, okay? But for this explicit case, we can compute explicitly the Gabor matrix so that we can explicitly compute the epsilon, depending on the time variable and alpha and beta, and you have this expression, as well as the constant c depending on t, alpha and beta. In this case, so we have that the control is explicitly, the control of the Gabor matrix is given by this exponential. You see that in the frequency we have this epsilon over 2 and epsilon in the time, where epsilon, written before, can be estimated easily and is controlled from above from pi over 4. And when epsilon is equal to pi 4, the threshold epsilon equal to pi over 4 is reached when b is equal to 0 and t is 1 over 2 pi alpha. Let me now come to visual representations of the Gabor matrix element. First, let me show you the results for the real heat equation. So beta is equal to 0 And in this case, we consider the atom given by zeta equal to 0. And you see in the picture 4 different instant times. The first, the initial case t equal to 0, where we start exactly with the perfect localized Gaussian. And then we consider the solution at the Gabor matrix at the instant time t equal to 1, 2, and 5. You see that as the time passes by, we obtain this anisotropic behavior, narrow in the y variable and broad in eta. Remember that in front of eta we have this epsilon t over 2, whereas in front of the y we have only the epsilon. Now, let me show you the case, the case of the complex heat equation. In this case, we have considered 2 examples of we computed exactly the entry of the matrix, again with z equal to 0, in the cases alpha equal to beta equal to 1 in the top row, and in the second, in the bottom row, we have alpha equal to 0.1 and again beta equal to 1 at the same times as before, 0, 1, 2, 5. So t equal to 0, we have the perfect Gaussian localization. And then you see that the anisotropic behavior comes up. In particular, the predominance of the heat parameter alpha with respect to the Schrödinger parameter beta, which is in the complex part, reflects on the angle between the semi-axis, which increases as you can see when alpha, the parameter alpha, reduces. And let me underline that when t, the time variable, increases, the support of our element spreads anisotropically along the semi-axis. Let me end up now by showing you also the study of the Gabor matrix for the wave equation. So we considered, in this case, we studied the propagator T sub T arising in the solution. Let me underline that the estimate of the symbol of the multiplier in this case is not nice as the ones we have seen before, meaning that the multiplier sigma belongs only to the Gelfand-Shilov class S0 infinity. And so the theorem we have seen above is satisfied for the case mu equal to 0, s equal to 1/2, and so we do not gain anything more than what was already known in the earlier result. You can see the off-diagonal decay at the bottom, the standard off-diagonal, Gaussian off-diagonal decay. So what we did is to compute explicitly, to get a better decay, the wave Gabor matrix for dimension d less or equal than 3. So you see this nasty expression. By means we can obtain a better estimate. You can see in the last but one line of the slide of the entry of the Gabor matrix. You see that we can obtain exactly the epsilon appearing in the estimate, which is given by pi over 4 for the time and pi over 2 for the frequency. And let me say that in dimension d equal to 3, we have a better estimate, which allows to see the spreading over the time. In fact, you see here that the element of the Gabor matrix is controlled by this exponential, and we do not only have the norm of the difference x minus y, but we have minus t. So we see the decay, which increases as the time variable increases. And let me end up simply by giving you a visual representation of the element of the Gabor matrix, again at distant time t equal to 0, the perfect localization, and then the spreading you can see as the time passes by. So this is all. Let me also refer to this paper with Gianluca and Luigi, where we consider not only the Gabor matrix representation of these propagators, but also another analysis using the Wigner representation of such operators. Thank you all for your attention.
Thank you very much, Professor Elena. We are very pleased with your presentation. Very interesting, very insightful. We would like to let you know that over 40 people were joining us in the session, and more on the YouTube channel. So it was a lot of attendees. Now the space is open for for questions. Feel free to write on the chat or unmute yourself. Yes, Juan Pablo.
Yeah, thank you. I have one curiosity, is that in the wave Gabor matrix, the last result, what happened when the dimension increase, like dimension 4, or in
We
general?
don't have any kind of result for d greater than 3, unfortunately, because we do not have the nice representation of, we relied on the representation of the density operator related to the Gabor matrix representation for the wave equation, which is possible only for d less or equal than 3. For d bigger, unfortunately, we cannot have any better than the standard, of course, decay estimate here, the Gaussian of diagonal decay, which holds for every dimension. But you see here that the estimate is not taking care of the decay varying with respect to the time, at least not here. We are not able to see a better decay when the time increases, unfortunately.
Thank you very much, Professor.
Yeah, and one last question is that if you have one example that where we cannot have a better estimate. I mean, that an example where it's impossible to have that frequency part.
Sorry, you mean that if is it possible to have something like this in the case of the wave equation? Is this what you mean? I mean, I think that the general theory holds only when the symbol lies in a nice Gelfand-Schirmer space. When, as for the case of the wave equation, we have mu equal to 0, the general theory doesn't work anymore. And in order to get better results, what we did is work exactly on the exact representation for which varies depending on the dimension, and to see whether you can get something better. So that is what we did for d less or equal than 3, but for the bigger, there is no nice, as far as I know, representation, so that we don't know how to get a better of diagonal decay, better than what we already have, actually.
Yeah, thank you. Yes, I mean, like, if there is some sharp estimate, if there
Sharp.
is this, yes.
These are, you mean, well, for the wave, no, but the heat equation gives exactly, in the case of the real and complex heat equation, we exactly get the exponent epsilon, which satisfied the decay. So exactly the powers are sharp. For the epsilon and c, actually, it is not possible. I mean, open question how to get precise estimates for the constant c and the exponent, the epsilon, the exponent. This is not known, actually.
Thank you very much, Professor. Lena, if anyone else would like to ask a question, please raise your hand. In the chat, they're asking if there is any link between the Gabor matrix and the Gabor operator in harmonic analysis. I don't know if you're aware of.
What is the Gabor operator? I mean, for me, the Gabor is Gabor frame. So the Gabor frame operator, yes, of course, because the Gabor frame operator is the one. I don't know if you are meaning the Gabor frame operator. I don't know other Gabor operators, actually.
Okay, thank you very much. That's
Sorry.
everything they wrote. So thank you, Professor. Yes, Duan?
Professor Cordero, thank you very much for the very nice talk, of course. I have a question. I think it was the very beginning of your talk, right? When you compare curelets,
Yeah.
curelets and Gabor frames, right? So I just wanted to know maybe if you can emphasize between the difference and what you gain when you consider your analysis with the Gabor frames instead of considering curelets.
Well, of course, in our setting, well, first of all, handling Gabor frame is easier than curvelets and shearlet frames. I didn't write down explicitly the expression, which is a mess. A lot of parameters come up to define this kind of frames, which, by the way, work only for the dimension equal to 2. Well, also because people were interested in dealing with images, and so maybe they focus only on that case. Anyway, Gabor frames are easier to be handled, less parameters, and moreover, you see in this slide that the comparison between the decay of the end largest entry of a line of a row of a column of a Gabor matrix compared to the shearlet case, we have super, especially when the mu is less than 1, super exponential or exponential like decay, whereas they only have a super polynomial decay, which make a very big difference once you have to represent these operators in a computer using algorithms, because in this case you have only you can represent only a finite number of entries, and of course for the sparsity, this exponential, super exponential sparsity says that you really need few elements that give you the information of the operator. That is why people look for sparse representations of operators.
Okay, thank you very much. Just because I just in the literature I just know curlets in dimension 2, right? They are not so much popular in higher dimensions, right? That's a point, right?
I
Okay,
think too difficult to handle, and I don't know if they have, by the way, results also for the bigger than 2. For shearlets, yes, but the general theory of curvelets, I doubt it. I think people decided in the end to drop these kind of frames because they were not so useful, and switch to wavelets and other wavelet-like frames, indeed.
thank you very much. And maybe just last question, if you have considered the analysis of Fourier integral operators, but with complex phases, following this theory of Mellin and Sjostran, right? This perspective.
Actually, Gianluca Giacchi with the Tramontana studied also these kind of operators. And let me say that Gianluca and Tramontana are now, I think, the main experts in considering operators with complex phases. So I would suggest that you could invite them in a further conference to talk about these aspects.
Thank you very much.
You're welcome.
Thank you very much. I don't think there are any more questions. So thank you again, Professor Elena, for accepting our invitation. It was an awesome presentation. Thank you very much. I hope you can join us in future activities. Thank you.
Thank you.
Dear Fred, are you in this? Okay, thank you, Fred.
Hello, Manuel. So our next speaker is Professor Aziz Beg. So Professor, if you are here, could you kindly share your screen with us?
Yes, of course, Professor, I'm here.
Okay.
Yeah, let me share my presentation. Is it visible or not? Yeah.
Can you make it a little bit large?
Okay,
Okay,
now,
it's fine. Okay. So
okay.
this talk is going to be given by Professor Azizbek from the Institute of Mathematics. It has written on the title, An Inverse Coefficient Problem for a Time Fractional Pseudo-Parabolic Equation with a Logarithmic Non-Linearity. Professor, we thank you for honoring our invitation, and we give you all the time. The floor is yours, so you may proceed.
Okay, thank you for introducing me. Hello, everyone. My name is Azizbek Mamanazar from Romanovsky Institute of Mathematics, which is located in Tashkent, Uzbekistan. And today I will present our work on an inverse coefficient problem for a time fractional pseudo-parabolic equation with a logarithmic non-linearity. And this work concerns the existence and uniqueness of the weak solution and also identification of a coefficient in a nonlinear fractional pseudo-parabolic equation. Yeah, it is known that pseudo-parabolic equations arise in many physical processes such as fluid filtration in porous media, heat transfer processes, and also fluid flows on non-Newtonian fluid flows. And we know that the classical representation of the pseudo-parabolic equation has a form of the one, and this equation differs from the classical parabolic equation with this term. So because of this term, this equation is called pseudo-parabolic equation, and and also we know that in many real-life processes, classical derivatives cannot describe the memory effects. So therefore, in the previous model, we replace the time derivative with the Caputo fractional derivative of order alpha, which is defined by formula 2. And this allows the model to capture history-dependent dynamics. And let me start our main problem in a domain omega of Rd with a smooth boundary. We consider the equation 3 with the initial condition 4 and the homogeneous Dirichlet condition 5. Here, dt alpha denotes the Caputo fractional derivative of alpha fractional order, and here a of x, b of x, and these functions are given functions. And our aim is identifying the solution of this problem and also this coefficient f of t of the problem using the integral form of our determination condition. And here the constant p is a real number which is greater than 2. And please pay attention to the equation 3. This equation contains this term. This term is usually called nonlinear term in logarithmic nonlinear term. And this term is interesting on the one hand. In many real-life processes can be modeled by this form of the nonlinearity. Such as inflationary cosmology, optics, geophysics, and others. In the modeling of the problems in these areas are modeled by this form of the nonlinear terms. So, and on the other hand, if u tends 0, we know that logarithmic function tends to infinity. From this perspective, this nonlinear term may cause some mathematical challenges during studying some problems for the equations, including these terms. So, and behave this form of inequality for these logarithmic functions, it can be proved using the properties of the derivatives, and from the inequality 6 it follows that in some sense logarithmic form of the nonlinearities can be controlled by power type nonlinearities. So it is naturally arises a question if we could control logarithmic term by power type nonlinearities, why do we need to study equations containing logarithmic nonlinear terms? But many studies showed that there are some differences between logarithmic nonlinearity and power type nonlinearities. For instance, in this work of Shen and Tian, which is published of Journal of Differential Equations, it was considered the problem 7. This pseudo-parabolic equation with the integer order time derivative and this form of logarithmic nonlinearity. And their approach showed that the solution blows up at infinity if we consider this form of the nonlinear equation. And the next study, if we replace the previous problem logarithmic term with this form of the power type nonlinearity, and if we consider this problem 8, there is some differences between blow-up phenomena of the solution. More precisely, in this case, blow-up phenomena occurs in a finite time. So this shows there will be some differences between power type and logarithmic type nonlinearities. Another example was published in this work, and in this work they considered this problem with time-dependent coefficient instead in front of this nonlinear term. And their approach showed that for the existence of the periodic solutions of the problem, the logarithmic nonlinearity behaves like the power type nonlinearities. However, if we consider instability of this periodic solution, then there arise some differences between logarithmic and power type nonlinearities. Can you hear me, Professor Frederick?
Yes, please, we can hear you. You are loud and clear.
Okay. Since in the present talk, we are planning to consider inverse problem for the pseudo-parabolic equation. So let me recall some known results on this direction. For instance, in the work of Professor Kampush and Shakir Aidos, the following form of the pseudo-parabolic equation considered with an initial and homogeneous Dirichlet conditions. And this equation includes this form of P Laplacian term and this form of nonlinear term, power type nonlinear term. And their aim was to recover the time-dependent coefficient of the equation 10 using the integral form of our determination condition. And in this work, they considered two cases for the parameter of gamma. For the positive, for the negative values of these parameters, they established local and global in time existence of the weak solutions of the inverse problem. And another approach has been done by Professor Różański and Berik Poltorabek, Niaz, and others. And they considered the following form of pseudo-parabolic equations with arbitrary operators L and M with discrete spectrum in a Hilbert space H with this form of initial and final conditions. The aim was to recover this right-hand side of this equation using this overdetermination condition. This work they proved that existence and the uniqueness of the solution and some assumptions on the given data. And I should mention that in this case, they considered linear form. And for the time fractional pseudo-parabolic equations with the non-linear terms, I would like to give information the work of Hampush, which was published in 2024 in this journal. And in this paper, he considered the problem 11 to 13 with this form of 14 with this form of the overdetermination condition. He aimed to recover this time-dependent coefficient from this problem. And however, to the best of our knowledge, inverse problems for pseudo-parabolic equations involving both fractional time derivatives and logarithmic nonlinearities have not been investigated in the existing literature, so we decided to consider this problem. More precisely, we decided to study the equation 15 with the initial condition 16 and the homogeneous Dirichlet condition 17. Our aim is to recover this time-dependent coefficient of the equation using this form of the overdetermination condition. Here, omega of x and e of t are unknown functions. Okay, the method is as follows. First, we reduce our problem to a non-local problem using the overdetermination condition, more precisely multiplying the equation 15 by omega and integrating the obtained equality over the domain, and using this form of the overdetermination condition, we can represent the unknown function f of t via the expression of the unknown function u. So it means if we put this expression of f of t into this problem, we will have some pseudo-parabolic equation with a non-local term, and we can consider this equation with this initial and homogeneous Dirichlet conditions. And we suppose that this integral is non-zero. And now we can give the definition of the weak solution of our problem. We call a pair of functions u and f as a weak solution of problem if it satisfies the following conditions. Condition 1, and this is the initial condition, and also for all 5 from this set of functions, and for almost every t, it should satisfy the following identity. And here f of t is given by the previous equality, and from here and to the rest of the talk, we will denote by sigma this value. P is a constant in our equation, and epsilon is any positive number. So before sharing our main results, I would like to present conditions for the given data of the problem. We assume the given data of the problem satisfies the following conditions, 21 to 27. So in our equation, we have this form of the function f, and f should be Lipschitz continuous. That is, there exists a constant, this is a Lipschitz constant, For all S1 and S2, the inequality 27 should be satisfied. And this is our notation is by these norms. We will denote the norms of the spaces, Lebesgue spaces LQ omega and LQQT respectively. So these norms defined by these equalities. And this is our main result. Under the assumptions 21 and 27, and together with these assumptions, assume that the following inequality is satisfied, and moreover, we assume that the power of the P satisfies this inequality here. 2 star denotes the Sobolev conjugate of 2. Then there exists a constant S and finite time T1. Our problem has a local in time big solution, and for this big solution, the following estimates are valid here. M1 and M2 are positive constants depending on the given functions of the problem. And our next result is about the uniqueness of the solution under the assumptions of theorem 1. The weak solution of the problem is unique. And now we will move the proof of the theorems. I will briefly explain the proof. So to prove the existence of the solution, we apply the method, Galerkin method. So we take an orthonormal system psi k in L2 omega, and for a given number n, we consider n-dimensional subspace Vn spanned by these eigenfunctions, and we will seek an approximate solution of the problem in this form. And here we have the coefficients Cgn of t. To define these coefficients, we will obtain ordinary differential equation from this equality, and also this differential equation should satisfy the following form of initial condition. Moreover, we assume this limit holds true, and here fnt and fnt approximate of the source function is defined by the equality 35. As a result, using the orthogonality of the functions of the family, we, from the system 33, 34, we will have the following form of Cauchy problem for the fractional differential equation. Here we denoted by this vector function, and we know that if this problem has a unique solution, if the right-hand side of the equation is a locally Lipschitz continuous function, so from the equation 33, one can see that with respect to the coefficients of the u, we will have some nonlinear terms arising from this term and also this. So to prove the locally Lipschitz property of this function, we only need to show the locally Lipschitz property of the logarithmic term. So to deal with this problem, we proved the following lemma. We introduced this function, and we extend continuously this function by defining this value at the point 0 by 0, and also we can continuously extend this function derivative of the function by demanding this equality. Under this extensions, the following inequality holds true, and using this inequality, we can prove the local Lipschitz property of the right-hand side of this equation. Then, based on the general theory of fractional differential equations, this problem can be solved for some Tn, which can be depend on n, this n, and after obtaining a priori estimates, one can prove that this Tn can be extended to the whole interval from 0 to capital T. And then now we will show how to obtain a priori estimates. And first, we will multiply both sides of equation 33 by this function and summing up from 1 to n with respect to k. And using this inequality, we will have the estimate 39, and we will estimate each terms on the right-hand side of 39. I will skip here the full proof of these estimates. Later, we will multiply the equation 33 by this function and doing the same using the 38 and the assumption 25, we obtain the estimate 40. And after obtaining some estimates for the right-hand sides of 39 and 40 and summing up resulting inequalities, we will get the following form of inequality. Here, the constants lambda mu, the coefficients lambda mu are defined by these equalities, and here, as you can see, lambda includes parameters epsilon 1, epsilon 2. These parameters arise when we apply the epsilon Young inequality, so they are any positive numbers. So by choosing these positive numbers, we should get the positivity of these coefficients. So for instance, if we choose these positive constants in this form to our 5k, here k is any positive real number greater than 1, then as a result, lambda will be positive, since in this case, lambda takes the form. And also in our theorem, we have the assumption 28, and using this assumption, we will have the positivity of the coefficient mu in equality 41. And now we introduce this form of notations, and after these notations, from the inequality, we can obtain this form of inequality, and one can see that this inequality implies this form of inequality, and our aim is to reduce our inequality some known like Grunwald type inequalities. So we are doing these steps. Here, y of t is defined by this equality, and applying the Riemann-Liouville fractional integral operator to the both sides of 44, and using the properties of the composition of the operators, Riemann-Liouville and Caputo differential operators, we will have this form of inequality. And next, skipping this term, we get inequality 46, and we don't have this form of Grunwald type inequalities because of n. So to obtain some known fact about nonlinear Grunwald inequalities, we will apply Hölder's inequality and then Young's inequality. As a result, we will have this estimate for the function y of t, and using nonlinear Grunwald inequality, we obtain the following upper estimate for the function y of t for the values of t, which is which changes between 0 and capital T1, and T1 is defined by this constant. And from 47, it follows that since y of t is defined by this equality, the following estimate holds true. Here C13 is not dependent on the n, and using this estimate, we proved the following estimators. These estimators are used to show like convergence of the subsequences to prove the existence of the solution. And using these estimators and also by the reflexivity of the function spaces, we will have this form of convergences. And also by applying fractional analog of Aubin-Lionis compactness lemma, we obtain convergence of the sequences UN strongly in L2QT, and particularly from this convergence follows that almost everywhere convergence of these sequences, and with the help of these factors and also Lionis compactness lemma, we can conclude that nonlinear term converges this term. So this justifies the existence of the solution of the problem, and for the uniqueness of the solution, we assume there exist two weak solutions, and as usual, we will denote by U and F their differences, and doing the similar steps as in the a priori estimators. After some computations, we will have the following form of Cauchy type problem. And from this Cauchy type problem, we can conclude that y of t equals 0. It means our solution is U1 and U2 coincides. So our solution has a unique weak solution. That's all. Thank you very much for your attention.
Thank you. Thank you for such a wonderful presentation. And we would like to let you know that 41 people joined your talk. Now it's time for questions. Please, if you have any question, you can write in the chat box or raise your hand or unmute yourself and ask questions. Okay, so Professor, for slide 45, the one, yeah, 45. So here, looking at the differential.
Sorry.
No, 44 rather. Looking at the differential equation. So let me see.
The first
No,
slide, you mean?
44. 44.
40, 44.
Yes.
Okay. This one, yeah?
Yes, yes.
Okay.
From the problem that we considered, you are saying that T should be within the interval of 0 to capital T.
Yeah.
Now, can the capital T also be 0?
Sorry.
Now,
Yeah.
now we are considering that T should be in the range of 0 to T.
Yeah.
0 to T, meaning that 0 is not part. But is there a case whereby we can consider the case whereby T is 0?
T equals 0, you mean, yeah? Sorry, I couldn't understand your question, maybe.
Now, I'm saying
Yeah.
that within the range, T is within the range of 0 and T. But in
Yeah.
this case, 0 is open, it's not closed. So I
Because
want to
we
find out, can we consider about a closed set or a closed interval?
okay. Thank you for your question. Yeah, I understood. I got it. Yeah. In this case, we have this initial condition also. The value of the function at the point 0 equals 0. So we can extract this point from this inequality. Yeah.
Okay, thank you.
Yeah. Thank you. Thank you for your question. Yeah.
Okay. So I don't think there is any more question. We thank you, Professor Azikbek, for honoring our invitation, and we would like to see you in future. Thank you.
Thank you. Thank you for organizers of the conference. Yeah. Thank you.
Okay. Listo. Yeah. Okay, Manuel, maybe can you try to share your screen, your presentation? Um, Very
Can you
good.
see it?
Yes, I can see well your screen. Uh, let's just wait 1 minute.
Okay.
Okay, very good. So let's continue with our scientific program. It's for me a great pleasure to introduce Manuel Alejandro Martínez Flores from the Department of Mathematics at the Universidad del Valle de Guatemala. Manuel is a young researcher working in analysis and partial differential equations. And during almost 2 years, he has been very active in the ICMAM Latin America community. So thank you for joining us in his talk titled Boundedness of Pseudo-Differential Operators on the Torus. Please, Manuel.
Thank you very much, Duban. Thank you to each and every one of you that joined to this presentation. So I will be talking about the boundedness properties of pseudo-differential operators on certain function spaces defined on the torus. This work has been done in collaboration with Dr. Duban. So I'll be sharing our results. So first, I'm gonna introduce the ideas and the reasons why we want to study these kind of operators. Then I'm gonna share with you some preliminaries and tools that are necessary for the topic. Also the Hardy and BMO spaces, which are important not only in this topic, but in harmonic analysis in general. Then we're gonna define the pseudo-differential operators on the torus. Then we're gonna study the boundedness in Lebesgue spaces, in Sobolev spaces, in weighted Lebesgue spaces, and in Hardy spaces. So first, let us discuss the general context. The theory of pseudo-differential operators is a fundamental tool in modern harmonic analysis. It allows us to study regularity of solutions in partial differential equations. They extend the theory of Fourier multipliers, and they provide a framework to study boundedness of such operators. In the Euclidean case, in Rn, the theory is well established and researched thanks to the very famous and fundamental works of Alberto Calderon, Anthony Sigmund, Blas Hormander, Charles Pfefferman, and many other mathematicians in this area. Now, just so we are clear with some notation and terminology, when we are using this curved inequality sign, we indicate that this inequality exists up to a constant c, and when it depends on a parameter, we use it as a subindex. We use the Japanese brackets to capture the asymptotic behavior of the norm without representing any singularity issues at the origin. And we use the multi-index notation, right? We have that for a multi-index, we simply expand the expression for each of the multi-index and the variables. And the length is just the sum of all its components. Okay, so in the Euclidean case, we have two parameters, delta and rho, between 0 and 1, and we consider the Hormander symbol class, denoted by Sm rho delta, consisting of smooth functions in Rn times Rn, which are the space and the frequency. And they satisfy the symbolic inequalities. That means that for every derivative we take in a space, we gain, we lose a delta factor in decay, and we gain an alpha arrow factor in decay for each derivative in the frequency space. Then the associated pseudo-differential operator is defined as follows: as the inverse Fourier transform of the symbol times the Fourier transform of the original function. And we simply denote the set of such operators as capital Psi M rho delta. Here is Pfefferman's classical theorem, which is really fundamental in this theory, which says that for parameters that satisfy this inequality and the order of the symbol that satisfies this inequality, then the operator is bounded from LP to itself for P between 1 and infinity, restricted. So the objectives in our work and what we're going to share in this presentation is to extend this result to the case of the torus, which represents unique challenges to the discrete nature of the frequency spaces, which is the lattice set n. And we want to formalize the symbolic calculus, extend the LP boundedness result of Pfefferman, and one of Alvarez and Huni, which we are gonna discuss in a moment. We're gonna establish conditions for boundedness in Hardy spaces as well, and results in weighted spaces following techniques of Paracantomita. Please notice that it is not possible to extend the Euclidean result to the torus by means of local coordinates. considering the torus as a manifold, because in that case we are restricted by the parameters, and that restricts our range of freedom. So we are going to consider them as separate cases. So for the preliminaries, we have that the n-dimensional torus, it can be defined as the quotient additive group between the reals and the integers, which we're going to denote by capital Tn. Moreover, it can be identified with the set 0, 1 to the n. Additionally, we have the quotient topology, and we have a restricted Lebesgue measure. You may notice that the total measure of the torus then will be 1 by the identification we just discussed. So we're going to work on Lebesgue spaces, particularly weighted Lebesgue spaces. So for a locally integrable function, we define the measure of its integral, and we use the usual definition for Lebesgue spaces using that measure. Moreover, we have the weak type definition, which is the usual definition for weak LP-LQ Lebesgue spaces with respect to certain weights. So we have that the measure of this set with the measure U must be less up to a constant than this expression containing the LP norm of the function. Okay, this is crucial in interpolation theorems such as Marcinkiewicz. Moreover, we also prove the weak L1 boundedness of these operators, of pseudo-differential operators on the torus. These are not included in this presentation, but they are also part of our results. So we have the respective Fourier analysis on the torus. We define the Schwarz space in the lattice Zn, which is the definition similar to that in Rn, which consists of rapidly decaying functions, such that they decrease faster than any polynomial. Moreover, we have the periodic Fourier transform, which is defined similar as in Rn. Just notice that it only takes values in the lattice set n. Thus the importance of defining the Schwarz space in this other lattice. And the inverse is now a series for the same reason. We can consider the space of periodic distributions, which are the continuous linear operators from the space of smooth functions on the torus. We can consider every function in LP as a distribution by the functional defined by the integral, right? Discrete distributions, which are defined on the lattice, are well defined, which is different from the case in Rn. Here we have that for each C in Zn, the functional must have a defined value. We then define the usual distributional derivative based on integration by parts, and the distributional Fourier transform, which is defined as in this expression. Because of these identifications, everything that we discussed can be studied in the sense of distributions as well as in usually defined functions. Now we define the Sobolev spaces for integers. We take k an integer, a positive integer, and we define the Sobolev spaces of all functions in LP with weak derivatives in LP up to order k, and we define the norm as the sum of the norms in LP of its derivatives. Okay, now we're gonna discuss the Hardy and BMO spaces. We adapted the Pfefferman-Stein theory for both Rn and the torus. We say that for an integrable function, f, it is in the Hardy space H1 if its Riesz transforms, which are defined as these expressions, are integrable, and we define the norm as the sum of the L1 norm of the function and its Riesz transforms. However, this definition is not as practical for our purposes, so we're gonna define the atomic Hardy spaces, which consist of PQ atoms. We say a function A is a PQ atom if there is a ball B such that the atom is supported in the ball, the norm is controlled by the volume of the ball, and it has vanishing moments, okay? Up to the order related to the parameter P. In this case, P is less or equal than 1. It can be shown that the atomic definitions are equivalent between each other. Moreover, H1 can be decomposed into the atomic definition, which justifies using any type of atom to define the space HP. That allows us to use interesting and useful properties that we're going to discuss in a couple more minutes. We have the BMO spaces. For that, we define the sharp maximal operator, F sharp, for a function defining in either the torus on Rn, and it is defined as the supremum of the oscillation, right? Where Fq is the mean of the function f in the cube Q. We define the norm of BMO as the supremum of the function f sharp. It is a very fundamental result from Pfefferman that the dual of H1 is the space BMO. Notice that here we require a special property of the image space because we're working with vector valued functions. In the sense that for every function in BMO, the functional that we defined before is bounded on H1. And if a functional on H1 is bounded, then there exists a unique function in BMO with the same shape. Now we are gonna present the complex interpolation argument of Pfefferman-Stein. We have that if a family of analytic operators are bounded in such a way between L1 and H1 and L1 and L2 and L2, they can be bounded or interpolated for P between 1 and 2. And if it is bounded from L infinity to BMO and from L2 to L2, we have boundedness for P in the remaining interval. Okay, now we're gonna define self-differential operators on the torus. We're gonna follow the framework developed by Roshansky and Turunen. Since we're working on a lattice, we are not able to use derivatives, so we replace them with finite difference. We have the forward and the backward finite differences, and we use the multi-index notation as before. So the toroidal symbol classes, again, we have an order M, parameters delta and rho, and we use the notation Sm rho delta in Tn times Cn, with functions now defined on Tn times Cn, smooth for every Xi in Cn that satisfy the symbolic inequalities, which are similar to the ones defined in Rn, just interchanging the finite difference operator with the derivative operator. Okay, now we define the corresponding differential operator, the same as before. The inverse Fourier transform, in this case with the series, because we are on the torus now, the symbol, and the Fourier transform of the function. Again, we use capital Psi, and if f is smooth, this series converges absolutely, and we are only dealing with the case when it is not. The definition suggests an integral representation of the operator with a kernel, which is expressed in the set of distributions without worrying about convergence, as the series in the last expression. Now, as part of our tools, we need to use integration by parts to obtain the K properties of the kernel. However, it is not possible if we are using series. So we use this following result from Roshansky and Turunen, that if we have a symbol in Tn times Cn, a toroidal symbol, there exists a symbol with frequencies in Rn such that the restrictions of the symbols are equal. And this extension is unique modulo S minus infinity, meaning that we can use these symbols and their kernels interchangeably. So, to discuss the boundedness in Lebesgue spaces, first we are going to discuss certain properties of the kernel. It is smooth outside of the diagonal, and we have that it decays faster than any polynomial when it is away of the diagonal, the kernel and its derivatives. Now we have a following result, which is similar to the one by Jorge Juni. Here and in the sequel, we're going to consider lambda as a parameter that encapsulates the difference between delta and rho, because in this case, we are going to allow rho to be less than delta. Thus, we need to take into account with this new parameter lambda. So, if the order of a symbol is less than negative n times lambda, and its derivatives up to order n halves satisfy the symbolic inequalities, then the operator is bounded from L2 to itself. Now, we're gonna show similar kernel estimates, similar to those used by Pfefferman and Stein. If we have a pseudo-differential operator with the usual conditions, we have that its kernel satisfy the following inequalities when we are in z and y less than sigma and x and minus z greater than 2 sigma. The difference of the kernels are less than a constant. In the case where sigma is greater than a certain epsilon, it is given by the compacity of the torus. However, in the case of where the radius is less than 1, it requires some technicalities more, so we require the order to be less than this expression. And we introduce a certain parameter rho here to control for the decay of the symbol. Okay, we have the weak type 1,1 boundedness. we have that if the operator satisfy this inequality with its order, then it is of weak type 1, 1. This result was proved for the general case of operators with operator-bounded kernels. That's why we defined everything in terms of vector-valued functions. But in this case, we're only presenting the one of pseudo-differential operators. Now, we present the results in H1 to L1 and L infinity to BMO. If a pseudo-differential operator has order less than this expression, notice that the order is similar to the one of Efferman plus the correction term lambda that we discussed earlier. We have that the operator is bounded from H1 to L1 and from L infinity to BMO. In this case, notice that we no longer require for delta to be less than rho, and it is taken into account by the parameter lambda. Okay, as little sketch of the proof, we want to uniformly bound the operator applied to an atom, and we're going to assume that the support of the atom has a radius less than 1, and we decompose the integral of the L1 norm into a local and a far apart part. For the local part, we use Holder and LQ, L2 boundedness, which can be obtained by using Bessel potentials. And for the far part, we use the cancellation property of the atom. That means that the integral is equal to 0. And the kernel estimates from the previous theorem to obtain the desired bound. Okay, here we see the kernel difference appears, and we can use the estimate. The proof for the L infinity BMO continuity is similar. Again, we decompose the ball and assume that the radius is less than 1. For the local part, we use again L2 LQ continuity. Again, it can be achieved by using Bessel potentials. And for the far term, we use the kernel estimates by choosing an appropriate constant for the BMO norm, thus completing the proof. Okay, so we have the main theorem of Lebesgue continuity, which is the boundedness from LP into itself. Here we have that the order must satisfy this inequality, which is the same as Pfefferman, plus the correction term, because we're not requiring delta to be less than rho, and we extend the existing theory to that case. Moreover, we can use Bessel potentials and Hardy-Littlewood Sobolev inequality to extend to LP LQ continuity when the order satisfies these inequalities in this expression. Now to discuss the boundedness in Sobolev spaces. We define the Bessel potential as the pseudo-differential operator with symbol of the Japanese brackets of xi to the power s. We say that f is in the Sobolev space WSP. Now s is a real number, not an integer. If the Bessel potential of f is in LP, and the norm is the LP norm of the Bessel potential applied to f. This definition is equivalent to the one presented when s will be an integer, so we use this one from now on. So, in the case of Sobolev spaces, the pseudo-differential operator extends to a bounded operator from WSP to WS minus mu Q for 1 less than P, less or equal than Q, all finite, if they satisfy all the inequalities in this statement, which is just a consequence of the LP-LQ boundedness conditions. Here we have the proof. It is pretty simple. We just decompose the operator into one that suits us. So we define a new operator which has order m minus mu, which satisfy the condition for LP-LQ boundedness, and we have the desired result. Now, to discuss weighted result, we're gonna define some maximal operators. First, we have the Hardy-Wood-Littlewood P maximal operator, which is defined as follows in this expression. This, when P is 1, we obtain the classical Hardy-Littlewood maximal operator. And now also we have the Pfefferman-Stein-Sharp P maximal operator, which is similar to the F-sharp definition that we discussed earlier, just with powers of P. As you may see, when we have P equal to 1, we recover the definition of F-sharp. Moreover, we have the Mockenhaupt weight classes, a pair of locally integral functions, UW, belong to the Mockenhaupt class if they satisfy the following inequalities, that they are bounded in the sense of the maximal operator when P equals to 1, and they satisfy this inequality when P is greater than 1 and less than infinity. This definition is very useful because the Hardy-Littlewood maximal operator is of weak type PP with respect to the weight W if and only if the weight W is in the Mockenhaupt weight class. That means we can characterize them in that sense. So we have a pointwise inequality in this case. This was using techniques developed by Park and Tomita. When the parameters satisfy these conditions, and we have a symbol sigma in the toroidal symbol class Sm rho rho, and the order satisfied this inequality, then we have that for all smooth functions, there is a relationship between the Hardy-Littlewood maximal operator and the sharp maximal operator of the pseudo-differential operator applied to the function, and it is described as below. Notice that we have a parameter R, and we can see that this implies boundedness in LP when we have a weight in the Mockenhaupt class of order P over R. As we can see by the properties of the maximal operator, we can bound the T sigma F by its sharp maximal function, and by this inequality, we can bound it by the maximal function applied to F. And since we are in a weight in the Mockenhaupt class, it is bounded from LP to LP in that weight. Now we're going to discuss the boundedness in Hardy spaces. In this case, we need the adic annular decomposition. We're going to decompose the space in rings, as in the expression of AJ. and the radius of each ring are determined by powers of 2. Okay. Now we have kernel estimates that are similar to the ones in the case for the Lebesgue boundedness. However, in this case, we are only estimating in each of the rings. Okay. Again, when the radius of the ring is greater or equal than certain epsilon, we can bound it pretty easily by the compactness of the torus. However, when the balls are small and we need a uniform bound, we require the order to satisfy this condition, which is similar to the ones we have been discussing before. And in this case, the kernel difference is bounded by a power of 2 and a power of sigma. So now we state the boundedness from Hardy space HP to the Lebesgue space LP, both with P less or equal than 1. So let us have a pseudo-differential operator as before. Assume that the order satisfies this inequality, where beta is a number between the usual requirement for the order and halves. Then the operator T, which is the pseudo-differential operator, is bounded from HP to LP for all P between 1 and a critical parameter P naught, where we have this relation over here. Now we want to discuss the boundedness between HP and itself. However, the image of an atom TA does not necessarily have compact support, so we need to decompose it into atoms. Thus, we introduce the concept of a molecule, which we will see cleverly named will be a sequence of atoms. So a molecule is associated with a ball B with center Z and radius sigma if it has an average of 0 and it follows the following decay conditions, which in summary, they mean that we can estimate the L2 norm by certain expressions regarding the volume of the ball. So to discuss the boundedness from HP to itself, we have that if M is a molecule with certain parameters, then the molecule is in HP, and its norm only depends on the constants that are in the molecule conditions, which will be the constants that appear in these inequalities. That allow us to prove the following theorem, that if T is a pseudo-differential operator with the usual conditions, then if we have this order, again, beta is another parameter between the usual requirement for the order and halves. We also require that the adjoint of T evaluated in 1 is equal to 0 in the sense of BMO, which is remind us of the T1 condition of Journet for boundedness in L2, for example. If we have this condition, then the operator T is bounded from HP to itself for P between 1 and a critical P naught, which is defined as before. Here we have another sketch of a proof. This proof can also be done in the context of operators with operator valued kernels. given that they satisfy the kernel estimates that we discussed before. So we take a P2 atom, which, as we discussed earlier, we can choose the second parameter of the atom as we prefer. And we want to show that it has a uniform HP norm. It can be shown that under the hypothesis of the theorem, the molecule, which will be the image of the atom, satisfy the condition of a molecule with constant that only depend on the operator or on the norm of the operator. Then we may use the L2 and LQ estimates to control the L2 norm of the molecule near the support of the atom, and the kernel estimates control the decay of the molecule away from the support, which is a similar technique that the one we discussed for the case of H1L1 and L infinity and BMO. So we're not gonna discuss them again. However, here we see why the condition of t, the adjoint of t applied to 1 equal to 0, since we can use the duality of the integral to obtain the cancellation property, which is required to prove that M is a molecule. And since it is a molecule, it has been proved that its HP norm is bounded and it is uniform. So here are some selected references, which are the papers where this result appear. We have other reference, some from Julio Delgado, in which he first extended Pfefferman's theorem for the torus, Pfefferman classic result, Pfefferman result for duality of H1 and BMO, Alvarez and Juni's theorems for continuity of the differential operators, where they first introduced these techniques, Alvarez and Millman, which are for vector valued functions, Jorge Juni's result on L2, Park and Tomito's result for weighted Lebesgue spaces, Rushansky and Turunin, where they developed the symbolic calculus on the torus and other spaces, Pfefferman and Stein's classical text in HP spaces. And that will be everything from my part for today. Thank you very much for attending this presentation and for your attention.
Okay, Manuel, thank you very much for your very nice presentation. So, are there questions for Manuel? Juan Pablo?
Yes, and thank you, Manuel, for your presentation. I have multiple questions, but at least for today, I have only two. The first one is that uh, um, do you have those boundedness conditions in terms of the kernel? Do you think it's possible to have in terms of the symbol, not for kernel condition, but symbol conditions, maybe on the order of the class of the symbol? That is the first question. And the second question, do you do you think that the results can be uh, unitarily invariant? Because if they are, it could be possible to translate these results into the dual of the torus, which is the integer lattice. And in fact, this is a strategy very used to prove boundedness of discrete operators. Thank you.
Okay. Thank you very much, Juan Pablo. To address your first question, yes, we have the conditions of the theorems in terms of the order of the symbol classes. Here M is the order of the symbol class, and beta depends on, bueno, and lambda as well, depend on the parameter rho and delta of the symbol classes. With respect of your second questions, I am not sure. I don't know if they are unitary invariant. I think it would be interesting to think about it, but I don't have any information in that regard.
Okay, very good.
Okay. Yeah. With respect with my first question, I mean, for example, in the results that you have, kernel conditions,
Mhm.
those results are in certain form equivalent to the symbol conditions, or what is the? I mean, what is the difference between the symbol conditions and the kernel conditions? The proof is different, or
Okay, I see. The symbol conditions imply the kernel conditions. Here, for example, we have a restriction of the order, which is the order of the symbol class. Rho is a parameter of the symbol class. And we require this order in the symbol classes because in order to obtain this estimate, this kernel estimate, we employ a boundedness property in L2 for the pseudo differential operator. So we require that the symbols satisfy the symbolic inequalities as in Huni's result for L2. Mhm. I don't know if that answers your question.
Well,
yes?
I would like to
Thank
say,
you.
Yes, Professor Rosidel.
yes, I met Manuel Martinez in Tegucigalpa in 2025 at Emalca, and
Yes.
congratulations to you. I'm very proud about your improving in mathematics. Congrats.
Thank you very much, Professor Rosibel. It was a pleasure to meeting you in Tegucigalpa last year. It was a great summer school. I hope we can meet again and share more mathematics. Thank you.
Okay.
Thank you, Professor Rosibel. I think Juan Pablo wanted to continue the discussion, right?
Was a mistake, but if we have time,
Yeah, yeah.
I have no
I
question.
think it's very nice. This is exactly the space that you can use to exactly to do this, right? To discuss between young mathematicians about the results and to know more about the work of others, right? So please continue if you want, Juan Pablo.
Uh, Thank you, thank you. It's a little for me. Could you explain uh, why it's useful the HPLP boundedness?
Okay, sure. Let me. Okay, here we are. Uh, it is it is useful because it allows us to explore the scale below p equal to 1 because when p is greater than 1, actually these spaces are the same, the HP and LP, with the definition we discussed before. So they are not as interesting as in the case of HP and LP, particularly the the space HP is of particular interest to us in harmonic analysis in general because it is linked to the families of maximal functions and they appear uh, in several um, scenarios. For example, as they can be also obtained as limits of the poison kernel, for example. That's why we study them. Mhm.
Thank you for everything. My last question was because there is a discrete hardy spaces, and my question that I have always is if there is some application of this boundedness in order to prove these results in the discrete case. Thank you.
Okay, I am not aware if they can be used, but I think it will be interesting to see if they work. Mm.
Okay, very good. I think this is a good example, right, of what we expect, let's say, from the lectures, from the conferences here, from the talks, because in particular, young researchers can share the results. They can meet other young researchers also that are doing, in particular, good effort to make good research in analysis. So just to say that Juan Pablo Lopez, who actually was asking some questions, also is ICMAM young researcher, right? But he's doing pseudo differential operators on the lattice, so he now is specializing. Please, Juan Pablo, I don't want just simplify all the activity that you are doing recently, but to my knowledge, you are doing discrete pseudo differential operator, right? So you are very much interested in discrete counterparts, right, of results that are available for pseudo differential operators and for other operators in right on arena and so on, right, and on the torus. So I think it's a good bridge, I mean, between both of you and the research that you are doing, right? Because Manuel knows very well the now boundedness properties of pseudo differential operators on torus. Maybe Juan Pablo is more specialist now in the discrete counterpart. Maybe we can have a meeting and we can continue discussing, because there are, of course, many open problems that one can try, right? For instance, just um, maybe giving the emphasis in one of the questions of Juan Pablo about the unitary equivalent, unitary boundedness, or when two operators are unitarily equivalent, right? This is very connected with L2 property. So here Manuel shows L2 LP boundedness, right? So maybe one can try to deduce from these results, and with the technique that Juan Pablo knows, right, the boundedness of pseudo differential operators on the lattice, using this the approach, joining the approach of Manuel and the approach of Juan Pablo. So I think it's very interesting. Of course, we can have a meeting, Juan Pablo and Manuel.
Sure.
Of course, we are like dual colleges.
Right, in all the sense of the word. Very good, very nice talk. So thank you. I think, are there more questions for Manuel? If not, I think then we can have a break. We can start at 12 in Colombian time and in the 18 in Central European time, right? With the talk of Federico Poco. And later, please, I invite you to join the plenary talk of Professor Anahit Galcian. Just an update that after the talk of Rakesh Palmar, we are going to have also another talk between 29 and 22 in Central European time. So I really invite you to all of you to join our sessions right after the break. So see you around. Thank you very much for joining the first part of our scientific program. Thank you very much. Okay. Okay, Frederick, maybe will you try please to share your screen? Very good. Will you please try to put your presentation in full screen mode? Very good. Maybe could you try to put your presentation in full screen mode? Oh, okay. It's visible enough, yes. It's visible enough. Control L you can use. Control L. Or if you want to see other people just in the way that you have now, or you feel more comfortable, of course.
Is that okay now?
It looks okay. It's okay.
It's okay.
Yes, it's okay. It's visible for us, I think. Yes. Or I think you can also go to menu, I think. And in menu, you have all the options.
But is this one okay for now?
It's okay, yes.
Okay. Then let's maintain this.
You can wait a couple of minutes. Also, Frederick, if you want to put in full screen, you can use Control L, Alt, in the right corner in the bottom part.
Is that okay now?
It's perfect.
Okay, thank you.
It's perfect. Yes. Okay, very good. So thank you to all the participants that have joined in this second session. It's with great pleasure that I introduce to Frederick Opoku from the Department of Mathematics and Kwame Nkrumah at University of Science and Technology in Ghana. Frederick had been researcher in the research group of analysis and PD in developing countries in ICMAM Latin America during the last year. So I'm very happy that we are going to hear from Frederick his talk about boundedness of Fourier integral operators with complex spaces on Fourier-Lebesgue spaces. So thank you, Frederick.
Right, thank you, Duvan, for the kind introduction. My name is Frederick Opoku from Kwame Nkrumah University of Science and Technology in Ghana. So in this talk, I'll be talking about boundedness of Fourier integral operators with complex spaces on Fourier-Lebesgue spaces. So the overview of the talk, I'm going to look at two things. The first one is to concentrate on Fourier integral operators with real-value phase function on Fourier-Lebesgue spaces. Then our contribution is we try to extend the boundedness of Fourier integral operators from the real-value phase function to the case of complex phase function. Now, this is the definition of Fourier integral operator with real-value phase function. So this is the Fourier integral operators with this formula. Now, in this case, we are going to get a symbol, and this one is the Fourier transform of F, and we have phase, the phase of the operator. Now, the phase and the symbol must have some properties that they need to satisfy before we can find the boundedness of Fourier integral operators. Now, the symbol must satisfy this inequality. Now, in this case, we are dealing with Kornberg symbol class of order M of type 1, 0. So if you want to estimate the symbol, it means that here, the symbol decay in eta and show growth in beta. But because we are dealing with Kornberg class of order M with type 1, 0, we are going to get this exponent 1 minus the norm of alpha. And the symbol is also compact support in X. Now, as I said, the phase and the symbol must have some certain properties that they need to satisfy. So in order to find the boundedness of Fourier integral operators with real-value phase function, then the first property the phase must satisfy is that the phase should be positively homogeneous of degree 1, different from 0, such that when you take the derivative of x and eta of the phase, the determinant of the results must be different from 0. In this case, you are taking alpha and eta from this space, and this space is a subset of this space as well. And the phase must also satisfy the spatial smooth factorization condition. Now, the spatial smooth factorization condition is a geometric property which allows us to make sure that the phase is linear. And now once the phase is linear, then we can talk about the boundedness of Fourier integral operators, such that when you take the derivative of the phase, the result, the phase, the gradient is constant on every affine fiber. Now let's look at examples of the phases. Now one simple example we can look at is when the phase is S times eta. Now, when you take the derivative of the phase with respect to x, we are going to get eta, and this eta is constant on every fiber on the space. So as we can also extend it to separated variable, and in the general case, when R is in the general case of rank R. Now, so this was the theorem that was proved in the case of Fourier integral operator with rate-valued phase function. Now we are saying that if the phase satisfy the assumption made, and the assumptions were non-degeneracy condition and the spatial smooth factorization condition, and the symbol must also be compactly supported in X, then if M is sufficiently negative depending on the rank, which is R, then we can assure of boundedness of Fourier integral operators. And this was what they proved. Now, this is the technical part of the proof, so we need to take attention to this particular one. I'm not going to prove the theorem, but I'll give the sketch or the idea of the proof. Now, so the idea of the proof of the rate-valued phase function. So the first thing to do is to conjugate the operator with Fourier transform. Now the idea is, or the consequence of this situation is that after conjugating the operator with the Fourier transform, now the phase is no more compact support in X. The symbol is no more compact support in X, and the phase is also not homogeneous of degree 1, where eta is different from 0. So the second thing is we apply relatable theory decomposition to the physical domain. This is to decompose the kernel into dyadic pieces. After that, we perform another decomposition, which is the angular decomposition, which is also partition the frequency domain so that we can do analysis on the local pieces. Now, we are also going to choose an operator, and such operator will help us to get the kernel of the operator, and by applying repeatedly of the operator to the function and using integration by parts, we should be able to know the bound of the estimates. Now we also look at the interpolation. They look at interpolation. The interpolation talks about trying to find if the operator is bounded as both at the extreme ends. That's when p is equal to 1 and when p is equal to infinity. Then we look at the intermediate exponent when p is greater than 1 and when p is less than infinity. So this is the operator that we considered in the rate-value case, and the bound that they also got is the scalar multiple of 2 to the power negative JR over 2. The R is the rank of the phase. Now, so this is our contribution, and this work is done in connection with Duvan Cardona and William Obin Dente. So the idea is that now for the rate-value cases, we are consider only the real parts without considering the imaginary parts. But to extend it to the complex case, then we must have a real part and we must have imaginary parts. So in this case, the imaginary part is different from 0. And we recover the real-value parts when the imaginary part is equal to 0. But before we can use the idea or the strategy that was developed in the rate-value case, then we must also make sure that we verify the complex value phase function so that the imaginary part will be absorbed by the symbol. So this was the theorem that we developed. We said that if T is a Fourier integral operator of order n, and in this case, we are considering complex canonical relation characterized by the complex phase function. Then, if we have this order, and this order is sharp, which was proved by Seeger-Suggestin in 1991, then we are going to ensure boundedness of Fourier integral operators with complex integral phase function. Now, one difficulty that we encountered as a result of this proof is that now in the real value case, they considered von Neubauer class of symbol of order M of type 10. But in this case, when you consider this same symbol, you are not going to get any results. And we realize that it works only for the real value phase function, but it does not work for the complex value phase function. So we consider the Amanda symbol class of order M of type 1/2 on 1/2, such that we are going to get a new symbol for the new phase. So this is the new phase, and this is the new symbol. And this phase must also satisfy the conditions of the phase function as was done in the real value phase function. It must satisfy the non-degeneracy condition and must satisfy the spatial smooth factorization condition. Now, this is the idea. This is the idea. After conjugation the operator, you realize that the phase here is a real value phase function. So in order to extend it, to the complex value phase function, then we need to introduce the imaginary parts. But we also assume that there exists a parameter T such that when we multiply the parameter by the imaginary part and subtract it, now this one will help us to verify the complex value phase function to verify the complex value phase function, so that the imaginary will be of the operator. So this particular expression is a complex value phase function, and this one is also a new symbol, which is the old symbol multiplied by the exponential of this function. But now we are going to get the symbol is going to get more oscillation, and for that matter, it is quite difficult as to how the boundedness could be. So when you find the derivative of the symbol, the oscillatory factor which is being added to the new symbol, you realize that the function is decaying by y, by show proof in eta. So this is the new phase function. So once we get our kernel operator, we are going to look at how we can bound this kernel operator. So we apply Littlewood-Paley decomposition. As I said earlier, this Littlewood-Paley decomposition will decompose the operator into a dyadic shell or a dyadic piece. So here the dyadic piece that we considered is this particular function. So the actual kernel is K of Sy, but because we decompose it into a dyadic piece, when we sum all the dyadic pieces together, we are going to get a full kernel. And once we also partition the kernel, the physical variable, it means that we are also partitioning the physical variable in the phase function. Now, as part of the partition of the dyadic piece function, if we consider a circle of center U vein J with radius 2 to the power negative j on 2, then we are going to get a cutoff function And this cutoff function also satisfies this estimate. But in our subsequent slides, we realize that as much as the cutoff function is contained in the U or in the ball, the norm of U is also less than 1. So here, in order to verify the phase function, we need to also linearize. We need to linearize the phase function by using the Taylor expansion. So we use the Taylor expansion to decompose the phase function into 2 parts. That is the linear part, which is easy to handle, and the remainder. So the remainder will be absorbed by the symbol, and the phase will be linear. Because the reason for doing this is that once the phase is linear, then we can assure of boundedness. But when it is quadratic or when it is exponential, it's very difficult for us to be know whether we are going to, or know whether boundedness of Fourier integral operator is guaranteed or assured. Okay. So here, once we have our kernel operator, then we need to integrate over the support. We need to integrate over the support. So integrating over the support, we have our phase function, we have our symbol. So the symbol comprises of the exponential function with the remainder, the cutoff function, and the new symbol. Now, the eta also functions, which is less than or equal to 2 to the power negative j on 2 in the case of the cutoff function. Now, so this is the operator that we are going to use. We use the same operator as was used in the real value phase function. So this operator will come up with a decay factor, and the decay factor will help us to control the norm of the operator such that we can assure of boundedness. Okay, so by repeatedly applying the operator and integrating by parts, we are going to get this decay factor and the integral of this whole expression. So this whole expression consists of the phase function, the symbol, which consists of the first decomposition and the second decomposition, then the exponential function, which is also consists of the verified phase function. So now, this is the decay factor. Now to find the decay factor, because first of all, we need to find the bound of the operator after the 2 decomposition. But to find the decay factor, it's quite difficult to find it in this way. So we find equivalent decay polynomial such that it becomes so easy to find the decay factor. So we use the fact that if 1 plus the norm of z squared or to the power negative n of this estimate, then we can also use the same analogy to say that the decay factor can also be written in this form. Okay, now our main task here is to see how we can find the bound of this expression. Now to find the bound of this expression, this particular symbol comprises of 3 different kinds of functions. There's a cutoff function. This one is the symbol when we apply the first decomposition, and this one is the exponential function, which consists of the verified part and the exponential part. So you want to see what happens when the derivative falls on each of them. Yes. So you realize that this symbol is in the class of the Hamada symbol class of order M of type 1,1. And the cutoff function is also supported in an angular part of this radius and satisfy this particular estimate. Now, so by applying Taylor, remainder, and all those estimates, we're able to bound them together. And by bounding them together, we got this particular estimate, which is less than this particular estimate, which is less than or equal to 2 to the power gm. And this particular estimate coincides with what was gotten in Nicola's case of Fourier integral operator with Weber phase function, which is 3.7 in Nicola's paper. Now we need to see what happens. We need to see what happens. Now we are going to find, as I said, we are going to find the norm of this. So as part of the norm, we have the bound, we have the decay factor, and we need to also integrate it over the compact support. So over the compact support, we know that M is equal to negative by kappa on 2. So say that when we multiply all these estimates together, we are going to get this particular results. Not forgetting that we are dealing with one particular cap. So by summing all the other caps together, which will give us this particular estimate. Now, so our analysis is saying that we concentrated on one particular part of the operator in one particular piece. Now we are going to consider the full operator, which is the summation of all the dyadic pieces. So the T is equal to the summation of the pieces that we have on L1 Fourier Lebesgue space. So we want to see if the function, if the operator is bounded in L1 or not. Now to do that, we introduce a smooth cutoff function with compact support in this region. Such that we introduce Fourier multiplier operator, and this Fourier multiplier operator extracts the part of the function which is near to 2 to the power g, and taking Fourier transform of that will give us this expression. So now let's bound this particular expression over the whole dyadic decomposition, and realize that by definition we can get this result. Now because this cutoff function has a compact support, then we can apply the Tonelli theorem, which says that we can interchange the integral sign and the summation sign. And once the chi or the cutoff function has a compact support, then this summation is bounded. And for that matter, when you apply all of the estimates, you are going to have this particular results. Okay, so to estimate for a single dyadic decomposition, we also look at the frequency in the localization of the Fourier operator. So in this case, we also introduce another cutoff function, which also has a compact with support. But the cutoff function is 1 within this region and is 0 also within this region. So in that case, we apply the Fourier multiplier operator to the function to extract the part of the function that is close to 2 to the power g before applying the Fourier operator to the function. Now, by taking L1 norm of both sides, then we could see that it's easy to obtain this particular results. Okay, so we need to sum over the g. Now, summing over the g, then the Fourier integral operator is equal to the sum of the dyadic pieces. So when we add the operator on the function f, we are going to get this result. Then we try to find the bound of the operator in the f. Fourier Lebesgue spaces. And we are going to step 2, because in step 2, we know that this particular result can be used in this part. Now we are looking at, now I want to look at when P is equal to infinity. So in this case, we construct a sequence of function. We construct a sequence of function in the abstract space such that the support of those functions is supported in this particular region. And now taking the norm of the sequences, terms are non-zero. And to assure of the boundedness, we also introduce another cutoff function, which will be added, which will be acting and summing them and finding the norm. So for the frequency distribution, we are going to add this cutoff function to each of the operator norm. And what the cutoff function, what this Fourier multiplier operator does is that it tries to decompose the Fourier integral operator into two. That is the Fourier integral operator whose symbol is of order -d on 2 and of type 1, 0. And we have also a smoothing operator. But in this case, the phase also functions as a frequency variable because the gradient of the phase or function closely to the phase, closely to the frequency variable. And anytime J and K are far apart, then the symbol vanishes to 0. So instead of summing from J greater than or equal to 1 to infinity, now we are summing over J minus 1 less than or equal to n naught because now it's finite. It's finite, and which will help us to get the boundedness when P is equal to infinity. Okay, now we want to look at the interpolation argument. The interpolation argument is that now if you look at when P is equal to 1, when P is equal to infinity, when the operator is of this order. Now we want to look at when P is greater than 0 and when P is less than infinity. Then we introduce a parameter x, and this parameter is a regularity of the phase function. It's a regularity of the phase which will be determined in the LP space of this form. So we are going to introduce an operator, and this operator in isomorphism in such a way that when you apply this operator to the Fourier reverse spaces with this parameter, the regularity of x, then we try to study the mapping of the Fourier integral operator from this space to this space, provide if and only if the Fourier integral operator acting on this part, composing on this particular operator, will take L Fourier integral operator of P to Fourier integral of P. Now, the order of the operator of T is M, and the order of the operator of this particular function is -2. So when negative S, so when you compose the two, you are going to reduce the order of the operator by -s. So in essence, the operator of this whole operator is given as, the order of this operator is given as n minus x. Okay, now we look at complex interpolation. So for complex interpolation, we try to look at when the Fourier integral operator is bounded in L1 and when it is bounded in L2. But for it to be bounded in L1, we realize that the Fourier integral operator does not behave nicely. And for that matter, we need extra regularity, which we have here as n plus pi kappa over 2. Now, we also look at the L square, and in this case, the operator behaves nicely. It's a special case. For example, when you consider the Poincaré theorem, it helps us to understand that the operator is bounded in this particular space. But we know that LP space lies between L1 and L2. So we use this particular equation such that when theta is between 0 and 1. So when theta is equal to 0, we are going to get P to be 1. When theta is equal to 1, we are going to get P to be 2. That is the endpoint case of the complex integration. And this will help us to integrate between the two spaces. So in conclusion, we can say that the boundedness for Fourier integral operators with complex value phase function holds when we have this particular order. And this particular order is sharp, which has been proved by Sigler-Soderstern in 1991. And these are some of the related works of the work. In the case of Duvan Cardona and Michael Ragansky with 111, and Fabio Nicola, Rodina, boundedness of Fourier integral operators. We also look at Martini and Muller and other related works. All right, thank you for your attention.
Okay, Frederick, thank you very much for your very clear presentation. I think the attendees have appreciated very much all the details that you've shown about the main theorem, right? So maybe are there questions for Frederick? Remember that for making questions, you can raise your hand, right? You can raise your hand. And we will allow you to unmute your microphone. But I think you can also unmute your microphone by yourself. Are there questions? Maybe Manuel? Are there questions for Frederick? Okay, maybe could you please, Frederick, share your presentation again? Right, maybe could you go please to the main theorem? Very good. Here, could you please explain the structure of this expression theta? I cannot
Please
hear
start the
you.
question again.
Could you please explain the structure of the function theta? What is theta in this setting?
Okay, thank you. So this is the idea. After conjugating the operator with Fourier transform, we have this phase to be the red value phase. So we then change the red value phase into complex function, meaning that we are going to get the real parts and the imaginary parts. So we introduce an operator that is negative tau of imaginary of the phase. So we are doing addition and subtraction plus tau of imaginary of the phase, the real value phase. So here we use the exponential function to take care of the part independent of the imaginary part, and we also absorb it with the part with imaginary part. So the part with the imaginary part will be absorbed by the symbol. So this particular expression is what we term it as a theta. This particular expression is what we refer it as what theta. Then we just introduce the s times eta. But for the theta is the rarefied version of the complex phase function. So once it's a rarefied version, then it must satisfy two conditions. That is the non-degeneracy condition and the special smooth factorization condition. Thank you.
Thank you, Frederick. I think was very clear from where theta comes. Maybe maybe for the people that is not for the people that are not familiar with harmonic analysis, could you please mention some comparison between how one makes dyadic decomposition or Littlewood-Palliser in Seeger-Stockstein and with respect to the analysis that you carried out here? You make a spatial Littlewood-Palli, right? But Seeger-Stockstein is Littlewood-Palli in frequency. Maybe you can emphasize this.
Please, which part?
Right, when you make a Littlewood-Palli decomposition in a spatial variable.
Wait, is that a question to me?
The point is, could you please clarify it a little bit why one use Littlewood-Palli decomposition in a spatial variable instead of using it in frequency variable?
Oh, okay. Thank you. So we consider the spatial variable because that one is compactly, that one has a compact support in X. And for the frequency variable, we don't look at the support. So we are working on the support of the X, the support of the physical domain. That's why we consider the physical domain or the physical variable.
Very good. Thank you very much, Emmanuel.
Yes, I have a question. Will you please go to the slide where you have the phi tau and the sigma tau, please? I think it was 16, I think. The next one, I think. No, the next, please. I'm sorry. Please, could you go to the next one where you define the new phase, phi tau and the new symbol, please? Yeah, this one. Thank you. I was wondering that I noticed that you require the phase to have positive imaginary part, but from what I see, you are defining a new symbol, right?
Yes.
Does the symbolic inequalities for the new symbol mean that the phase has imaginary part, or there could be they're not equivalent, let's say?
Okay, so this is the idea. After absorbing the imaginary parts, you want to see what is happening because the imaginary parts will introduce a new oscillation. So looking at the decay, you want to see if we are going to get a boundedness as a result of the more oscillation that is now introducing to the old one. And we realize that when we find the estimate of the new oscillating factor, now this estimate is also decaying in what? Y. Decay in Y and show growth in eta, meaning that it's also bounded. So the idea is that the new oscillating factor that we are just interested is not going to blow up. It's not going to blow up, though it's a new oscillation that we are getting, but it's also bounded. It will die out.
Okay, thank you.
Okay, very good. I think it's very nice to have this kind of good questions from young researchers in harmonic analysis. I think Juan Pablo is there also. Juan Pablo wants to make a question, or I don't know, Julio. Okay. Okay, I think the attendees are very happy with your presentation, Frederick. Thank you very much. I think it was, of course, a very nice presentation.
You're welcome.
Very good. So I think we have with us our next plenary speaker, Professor Anahit Galcian. But maybe Professor Galcian, maybe we can wait until 19 in Central European time to start your talk. Maybe we can connect again at 1850 to follow the talk of Professor Anahit Galcian. So thank you very much. Hi, Professor Anahit, how are you? Thank you very much for joining us again in the ISAAC-ICMAM conference. I think.
Thank you. Thank you. Unfortunately, I am now in a hospital
I see.
and I am delivering from hospital. I'm sorry for this,
Sorry to hear that.
but I will be good. It will be
okay.
okay. I don't know, some problem with my microphone. I will correct now.
But we can hear you well, I think.
Oh, you can hear me, right?
I can hear you well, yes. There is not a problem.
Yes, we can hear you. Right.
Okay, great. Then see you in a little bit. Yeah.
Right, maybe 10 minutes, 15 almost, to make the proof of your presentation. Thank you. Thank you for joining us early. Okay, so to all the participants, we are going to continue in 10 minutes. In 10 minutes, so you have the time to make a coffee and to come back. Thank you very much. Okay, Professor Anahit. So maybe okay, so we're going to stop sharing our screen. Very good. Maybe I think, Professor, you can unmute yourself.
Okay. Oh, thank you.
Much.
Can I share my screen?
Please share your screen, and I will leave you with Manuel Martinez, who actually will chair your session, young mathematician from Guatemala. So thank you very much, Professor Anahit Garcia, for joining us by second time. I think you were also in the first version of this conference, so thank you for your support.
Yes. Thank you for invitation. I really very glad to deliver talk at this conference and support the community. Just a minute, I have here technical some problems. I will just discontinue. Sorry about that. Just 1 minute. So if
Don't worry, Professor.
yes,
Thank
yes. Okay, sorry about that. So thank you very much for the invitation. I'm really happy to join you. Unfortunately, unforeseen circumstances for me, I had to visit doctors in different city, and now I'm delivering my talk from hospital setting. It just some checkup, but anyway, I apologize if some interruption will be, hopefully not. But just probably if somebody comes in, I don't know. So I got some separate room for me. So hopefully nothing will happen before that, because I have another appointment, doctor appointment in 1 hour. So that is why I cannot do it from hotel. So I should be in hospital.
There is
Okay.
no problem, Professor. Thank you very much. Thank you very much again for accepting our invitation. We're very glad to have you here with us today. Professor Anahit from University of Texas, Rio Grande Valley, from the United States. Thank you very much for joining us. And her presentation is titled Solutions of Semilinear Klein-Gordon Equation in the Space-Time of Black Hole with Variable Mass. Thank you very much,
Okay.
Professor Anahit. The time is yours.
Okay, thank you very much. So as already mentioned, I will talk today about solutions of semilinear Klein-Gordon equation in the space-time of black hole, and then we assume that mass is variable. This is a joint work with Dr. Karen Yagjian from University of Texas. So just a short abstract about my presentation. We are going to consider propagation of wave in the space-time of single black hole, and we assume that Schwarzschild radius is static in this expanding universe. And more precisely, we are going to talk about solutions of linear and semilinear Klein-Gordon equations. In our research, we assume that universe is expanded with acceleration and that the mass of black hole is variable, so it's changing in time. The main, we are going to apply Yagjian's integral transform approach, which makes it possible to bring the problem with unbounded time down to the problem with the bounded time. Do I need to go to full screen? I am sorry, I didn't think about that. Is it okay like this, or I need to move to full screen mode?
It is fine like this if that is what you're comfortable with.
Okay.
It's fine.
Okay. Okay, thank you. And let us start with introduction. The line element or a metric in this space that we are going to continue is given by the following equation. In this setting, you can see the RCH. This is a Schwarzschild radius, which is defined as follows. 2gmbhc square, where g is a Newton gravitational constant, c is the speed of light in vacuum, and m is just a constant. Also, in this metric, you see the scale factor, which is a squared t. In our case, we assume that this at, which is a scale factor, is equal ac, like some constant multiply the power function t in degree L, and we assume that our L is greater than 1. For just simplicity, we will assume that the constant is equal 1 and c is 1 also, it's just a constant. So anything else here? So here we have just the spherical coordinates in this case, yeah. As I mentioned, we assume that our universe is expanding with acceleration. There is no doubt that universe is expanding. By now, they say that it's already in some like experimental physics. They got even Nobel Prize for proving that our universe is expanding. So, and we assume that it's expanding also with acceleration, and which we assume that the mass of black holes will be also changing in time. There is a paper by Farah who suggested that to assume that the gaining mass of black hole is proportional to the scale factor raised to some power of k. We will set the k equal 1, and consequently, we assume that Schwarzschild radius is static. So in the paper from 2016 and 24 papers, the Yakjian proved that the black hole with static Schwarzschild radius embedded in Friedman, Lamatre, Robertson, Volcker space-time with de Sitter's case scale factor. So he studied such equations in this space. De Sitter scale factor is exponential space factor. So on the space with this such scale factor in the metric, is called de Sitter space-time. It's just one of the models of universe, and in the Friedman, Lamatre, Robertson, Volcker space-time. So we consider another family of the Klein-Gordon equation for the self-interacting space waves with the mass term, which is ingoing redshift, and it's proportional to the Hubble parameter. This quotient, so derivative of AT divided by AT. So the AT is a scale factor. In our case, I just remind you, it is T in L degree. And so we assume that mass term MT is given as follows. So it depends on T variable. And we assume that MC is just given by this. It's a constant. The equation under consideration that we are going to consider is the following equation. So it's a second order equation with some t, the t in denominator. So we have some problem here in denominator. That's why we are going to start with t greater than 1. So to avoid that, then we have the scale, the terms which is associated with the scale factor in the metric. And then operator A is the operator, which is given as follows. So let me just remove this off. Okay, sorry about that. AX dx is a differential operator in the spherical coordinate is written as follows. Here you see the radial derivatives. And also we can see this delta S2 is a Laplace operator on the unit sphere. Also, we have some additional terms here, and also we have a right-hand side, and we will talk about this psi function just in a minute of the case that we are considering. So this is equation of second order, and with the this setting. So we are going to consider that equation. According to the lemma from the Yagjian's paper from 24, the space-time of the black hole with static Schwarzschild radius is the only one that dissipates the waves independently of the location in space. And this is just related to cosmological principle. So the equation above we can generalize as follows, replacing the terms that here we have on this side that contain just the psi function without derivative with some potential VRT notation. So VRT is a potential which is from here. And it's included also the gravitational potential. So the term psi x psi represents the self-interaction of the field. So now we just rewrite our equation in this form. So you can see second derivative respect t, then first derivative respect t, then we have this differential operator plus something with the potential. And then we have a right-hand side, of course. Now if we consider the radial null geodesics of the space-time when L greater than 1, that was the assumption for the scale factor, as follows. AT is just this function, and it's clear that A infinity is this, and it's a clear relation that this relation is true for any t from 1 to infinity. And we are going to consider waves in the exterior of black hole, that is any x from the three-dimensional space when the x is outside of this black hole, yeah? So the choice of the initial data which supports sufficiently distance from horizon of the black hole allows us to avoid manifold where the equation is degenerates, because we have such problem in the equation. So we assume that support of initial functions, so Cauchy initial conditions, are inside of such space outside of the exterior black hole. And moreover, so this RID is something even larger, okay? And this is exactly the part in the exterior of the black hole. So we assume that initial functions are from the outside. And to introduce our results, we need to set also some space. And first of all, let me remind you just the notation. This notation will denote the Sobolev space. And we denote by B infinity is the set of all smooth functions with uniformly bounded derivative of any order. So the space of the functions that have a uniform bound. Sorry about this. Okay. And we assume that we are going to look for solution in the space of X, which contains all function psi from continuous from 0 infinity to hs, and psi norm we define as a supremum T gamma and norm in Sobolev space, and we assume that this norm, we just consider it such functions so that this norm is greater or equal R, so it's bounded. And the metric in this space define it as follows, again with some weight, and we assume that T is from 1 to infinity, we assume from the beginning. So this is the space where we are going to look for the solutions. What we are going to do, we are going to apply integral transform approach developed by Yagjian. Then we can recall the paper from Nakamura from 2014 and 2015 on the approach to the semilinear Klein-Gordon equation in the Friedman-Lamartre-Robertson-Walker spacetime based on the energy estimates. And what actually this integral transform does, it allows us to bring the problem for unbounded time down to the problem with the bounded time. And this is possible since the space-time has permanently restricted domain of influence, so we can do that. Now, I will be trying to state the problem here, but we need more notations. So I already assume we already introduced the RID such that this radius is greater than Schwarzschild's radius, and for every given psi0, psi1, so psi0 is from HS and psi1 is from HS minus 1, we assume that those data are satisfying. The supremum of this is in this set, which is inside of exterior of black hole. So the problem is to find a global solution which will belong to such space of this equation, of the equation under consideration, and such that the support of the solution will be in exterior of black hole, and at point 1, the solution will satisfy to given initial functions, so psi0 and psi1 respectively. So this is the statement of the problem. So in our equation, we have a potential term here, and then we have a right-hand side, which will be nonlinear part, via psi, which depend of x psi. So this indicate nonlinearity. So we are going to make some assumptions about V and then nonlinearity. So about potential time, we assume that the potential V belongs to this B infinity space, and it is such that it satisfies certain inequality bound. So for given S, we can find some constant, positive constant, and then delta strictly like positive or 0, such that the action, this norm of potential times the function in the Sobolev space can be estimated by this given via estimate of the function. So the action of the potential on phi, we can estimate via this function on the right. So this is some negative degree and then positive constant. And that can be done for any t from 1 to infinity and psi from this Sobolev space. And we assume that the function phi has a compact support. So this number, this constant epsilon pi, can depend on the distance between the boundary of sphere and the black hole. So that constant is depending on that. What about the nonlinear part that we have on the right-hand side? We will say that function psi, which is smooth in x, is Lipschitz continuous with some exponent alpha greater than 0 in the Sobolev space if support of this psi capital is inside of support of psi, and then there is a constant such that this inequality is true. So on this side, we see the difference between the nonlinear function, it evaluated by the norms of the function inside. And there's some very known examples of such a function that can be is continuous, Lipschitz continuous with the exponent alpha, are the terms like psi or this one, like psi in 1 alpha plus 1 and or just a product like this. this type of nonlinearities are of the special interest, and they are exactly Lipschitz continuous with exponent of alpha greater than 0. Our first result is about this equation with the large mass, physical mass. So we consider the equation that under consideration was this, and I would like to remind you that t is greater than 1, so we have no problem in 0, also here. And we assume that our initial conditions given for t equal 1, and potential is satisfying to the inequality I introduced above, that v times psi is bounded by t in some minus delta degree and the constant and the norm of the function. And we assume that this delta that we have in the inequality, let me go back to show you the delta, this delta for potential, in our case, we assume that delta is equal to. And we assume that physical mass of the field, which is this mc square, is large, is greater than 3L minus 1. So L is this constant, which is related to the scalar factor in the scale factor in the metric. And we assume that nonlinear psi here, this nonlinear psi x pi function satisfy condition like it's Lipschitz continuous with some alpha, with this alpha exponent. So nonlinearity exponent is greater than 4/3L minus 1. And also we assume that Cx0 is 0. That is our assumption. Also, we know that if we assume if epsilon p, it's a constant from potential, and also the norms of initial conditions are small with some s, like in the Sobolev HS space, where s is greater than 3/2, then the Cauchy problem, the one we already set it for the equation that we have, has a global solution, psi, which belongs to this space. If m is this number, so here you can see mc is a constant, and then we have this L is coming from the scale factor, and also it's of course in the equation, then the solution psi belongs to the X space that we already introduced with some gamma less than L. So the space X was the set of all functions that are bounded by some weight. If you recall, I like to show you to remind you this space. Yeah, here. So the X space was the set of all psi functions which are continuous here from this space, such that the norm is given by supremum T gamma psi, and this norm should be bounded. So the gamma is from the space. So why I'm reminding you, because in this theorem you can see the gamma. So this gamma comes from the space, and we assume that gamma is less than or equal to L. So L is the exponent of coefficient in the equation. And then such that if alpha, so this alpha is a exponent of nonlinearity. So if alpha satisfy to this inequality, and if then gamma from this will follow that the gamma, which was in the definition of the space, will be greater than this, and then for m greater than 0, and if while L will be greater than gamma and greater than is from m greater than equal 0. And the another estimates if alpha, this nonlinearity greater than this, then gamma has to be between these two numbers. So once again, once you have a alpha, everything is fixed in this inequality, so we can build space for the m which is greater than 0, and from m equals 0, the gamma has to be between these two numbers, and the gamma should be less than L. And the solution psi will decay according to the definition as follows, because it will be in the space of X. So psi will be satisfying this inequality. So it will decay when t approaches infinity. That was the theorem about the large mass. The similar theorem is true also for the small mass. In this case, we consider mass small, and the equation is the same, and also we consider initial conditions psi 0, psi 1 from Sobolev space. In this case, we assume that delta is greater or equal to, so we can allow any delta greater than 2 or equal. And we assume that the physical mass is small, which is this condition. So 4mc is less than 3l minus 1 squared. And then we assume that no linear terms satisfy condition L with exponent alpha, which is greater than this number. So now again, what we have in this number, as you can see, L is given once we have equation. Then we have psi 0 equals 0. I'm sorry, I need to get the water, just a minute.
No problem, Professor.
I apologize. I have asthma, and so that's sometimes it starts. Okay, sorry about this.
No problem, Professor.
So we are
Thank you.
introducing the, thank you. So we are introducing this theorem for the small mass, and so for the small mass, we also prove the global existence of the solution for s greater than 3 half. And interesting, in delta equal 2, then the solution belongs to this X space with gamma less or equal n L, and gamma should be less than this number. That means the solution psi is decaying according to this inequality. So psi xt has to be less than equal, will be less than equal this function by definition of the space X. So, and again, we see it's a decay. If delta greater than 2, then we have to choose gamma, which is minimum between, less than equal minimum between two numbers. So one number is L, and the second number is this. So the gamma has to be this chosen like this. Again, the gamma is the exponent that we have the weight function. I mean, this is a weight function in the definition of space X. That was the main, that were these results. And now I will talk about some remarks and maybe introduce some details of the proof. First of all, the first remark, if delta greater than 2, then and this condition satisfies, so then gamma will attain its largest value equal L. So gamma is the exponent from the space, and L is the exponent on the scale factor. So if this condition is satisfied, these two inequalities, then gamma can be equal L. They just can coincide. So the results of these two theorems for small mass and large mass in the case of mass of black hole is equal 0, agree with the previously known. If we note, we can calculate this limit when m approaches 0. So this is mass of black hole. If m approaches 0, this number is infinity. So then there is known paper with Tsutaeva-Kasugi that proved that for solution of semilinear waves equations, that is in the case of operator is the A is just a delta operator and the mass of black hole is 0. And nonlinearity is this type, psi 1 plus alpha. And then if m is also equal 0, then blow up in finite time can occur only for alpha greater than z, for all alpha greater than 0. So the blow up appear for any. In our case, we have gamma, you see, less than this number. So let me just go for, yeah, no, we have this number, so I can, oh yeah, here. So you see we have a alpha greater than this number, and we prove that we have a global existence. But if we assume that mass, but if this, if mass of black hole is 0, then we get infinity, so there is no global existence, which agreed with the previous result of obtained for the semilinear wave equation. Of course, we have a Klein-Gordon equation, but if we assume that m is 0, then we arrive at exactly the case. So that was the comparison. And for the semilinear Klein-Gordon equation, when we have a operator in equation is delta, and Schwarzschild radius is 0, and we assume that potential is 0, and if psi is a gain of this nonlinearity, so the psi is nonlinear function psi 1 plus alpha, this type of Klein-Gordon equation was considered by Aslan, Ebert, and Reisig, and they apply partial Fourier transform and split phase space into 3 zones. In particular, in that paper, they proved that the condition that alpha has to be greater than this number is necessary for global existence. So they consider it the case without potential, without like Schwarzschild radius, but they have interestingly got the similar exponent that we have. At the same time, the decay rate, which is given by this theorem for the small mice, coincides, yeah, like I mentioned, with this exponent coincides with the decay rate that they got in their paper. More comparison, Natarion Sassane in 22 obtained exact decay rate for the solutions to the Klein-Gordon equation in the de Sitter space time with flat Friedman-Loberth-Robertson-Volcker form. For the derivative of the solution to the massless equation, cosmological region of Reisner-Nordstrom de Sitter model under some assumption on the boundedness, they prove that L infinity norm has a decay at infinity. And then in that case, but they assume that mass and charge of the black hole is static, so it's not variable. That was the comparison. Now, another remark, the theorem for the main results can be extended to the equation like this. When mu is some parameter which is not necessarily relevant to the dimension of the special variable. So in our equation, we have a mu equal 3, which is related to R3. But one can actually extend this to the sum equation with parameter mu. And so this way we can extend this to n-dimensional black hole. Also, to derive better estimates at infinity, one can appeal to the estimates in homogeneous Sobolev spaces or to Giliardo-Nirenberg inequality. So we can extend this result to this. Now I have some time, so I may go over some some steps of the proof of the first theorem of large mass for large mass. So how we prove this theorem? So first of all, we apply Liouville transformation and use representations of solution to the linear equation. Then we derive decay estimates for the solution. Then we derive estimates for integrals of the kernel function of integral transform containing Gauss hypergeometric function. So I will show just in the next slide this all kernels. And then our proof completes the Banach fixed point theorem using the Banach fixed point theorem. We prove existence of the solution of the semilinear equation. So those are the main steps. And here are some details. So first, we consider linear equation that has just a linear function on the right hand, like here f function. We consider linear equation. And the first, we try to eliminate this mass term in the equation using partial Liouville transform. So partial Liouville transform is we multiply by some just time-dependent function uxt, and then we try to see what happened in that case if we try to eliminate actually this mass term. So if we just replace psi using this product, we will arrive at the following equation for u. And as you can see, we have this last term here, which contains the mass, this part, the factor in front of u. We are going to look for the omega such that this is 0, and this way we will eliminate the mass. Of course, the mass will be presented somehow, but not in the equation. We try to look for omega t as a power function, and then it will lead the equation that this equation will lead to the fact that to this equation. So if you put instead omega tk, then you get an equation for k, which can be solved easily, of course, quadratic equation. And so we will have a 2 powers k plus and k minus such that they actually reduce this equation to 0, the equation above. So we consider the equation with L greater than 1. So that was our assumption. That implies that we are going to consider 3 cases. First, we consider that MC is less than this. Then we have a corresponding K. Then we have a MC equal to this. Then the square root will be 0. So we will have another K, and then we have a third case when this M is greater than 3L minus 1. Then that will lead also correspondingly square root will be different. So if this is greater, then that will be negative, yeah, under square root. So we say that mass is small when mass of black hole less than this number, and while in other cases we say that mass is large. So that will be the distinguishment. Then we arrive at generalized Euler-Poisson-Darboux equation like this. So this is equation above, the one we have here, without this part, without the last part here. And then we replace omega by corresponding t power function. So if we do that, then we will arrive at something like this. So here is t in minus k plus minus. And here also corresponding, this comes from the equation for omega. So we denote mass capital, these two constants. So this m plus and m minus, the sum, we call this also mass, which is given by this equation. And then for the case of small mass, this number has to be less than 1 minus 3L squared. And then we have several inequalities for large mass, small mass that we have to use in the future. So now we concentrated on this equation. And we set initial time epsilon equal 1 in the formulas of that we have in the paper from 2021. And so we assume that I'm going to use those notation. That's why I'm introducing this. This phi function is a function t in 1 minus L degree. So once we have this phi, we can introduce kernel function which will be used in the representation of the solution. So in this kernel functions, you have a e, k1, k0. Here, what I just like to talk about these kernel functions. These are the kernel functions that will be used in representation of the solution. And here you can see phi, which is the function which contains this power function. And f is Gauss hypergeometric function. So those are kernel functions. E, K1, they all contain some, contain Gauss hypergeometric function, and also some expressions containing this phi function, which is related, of course, to the equation, the coefficient of the equation. So this K0 function is more complicated, has a two Gauss hypergeometric function, and we also define some another kernel. So I just would like to introduce those kernels so you can see that this just involve hypergeometric functions, but you have to work really very carefully in the estimation of those kernels in the future when you prove this result. So in these new notations, we can rewrite the equation under consideration in this form with this new m masses. And now we are going to assume that v function solves the following Cauchy problem. So v function is a function on xrb, so b is some parameter. A is our operator, and what is interesting, so we choose also VR. We choose solves only Cauchy problem with the first initial condition. The second initial condition is 0. And similarly, what we are going to do, therefore, when we have a phi function, we can also write this. Okay, it's almost same. So v phi notation, we assume that the v phi solves this. So we assume these two conditions. And then the function u, which is defined by this. You see, this is a representation of the solution of the equation above here. The only thing here, we have the kernels that we introduce, E, K1, K2, and also you can see VG function, VU1, VU0, and I will talk about all this. So VG, VU1, VU0, and those functions actually are the following. So this formula gives the solution of the following problem. So here you can see the equation that we have. Also, there is a right-hand side, the G. So we have a VG, which corresponds to right-hand side. And then we have initial conditions, U0, U1. Every time when we say VU1, that means this is solution of such problem with the first initial condition. So if we say U1, then here has to be U1. When we say U0, then initial condition has to be 0. So once we have the kernels, we can write the solution using this formula. This actually was already proved. So we studied this Cauchy problem for the equation that we are considering through the integral equation. So to define that integral equation, we have to appeal to the operator G, which is given us following: K times EE, where E stands for the evolution, fundamental solution for evolution wave equation in exterior black hole in the universe without expansion, as follows. So V is just the EE to the function, where V is the solution of this Cauchy problem. So F is a function first initial condition. So E is this, and the K is given by this integral. So this kernel was introduced before, so the K is this. So our G operator is exactly this. So in this case, also using those representations, we are going to obtain estimates. So we split our problem in several parts. So the first, we assume that the Cauchy problem has has an initial condition, but it's linear equation. So on the right-hand side, we have a 0. So using this representation of the solution in this case, we obtain the estimates for the weighted Sobolev norm for this type of solution. So here we have an initial condition, psi1, psi0. Those are those conditions that we have from the beginning. So for this type of problem, when we have a linear equation 0 on the right-hand side, we obtain such estimates. Then we have to obtain the estimates with 0 initial condition, but with potential term, and and 0 right-hand side. So we have a 0 potential, we have a with potential term. So we obtain a solution estimates for solution when we have a potential term. And so if we have this, we obtain such estimates, and all these estimates based, of course, on the investigation of for obtaining estimates for Gauss confluent hyperbolic function, and also the next we also have to do same thing, like we obtain it estimates for the weighted norm when we have a nonlinear term presented. So here is psi, so present, and the G is operator that gives us solution. So we obtain some estimates for that case. Again, the 0 initial conditions and with the presence of nonlinear term in the equation. So that we obtain, and then we consider now the following integral equation. So psi equal the psi ID, which we already have estimates. So this is the notation for the solution with initial condition, but 0 right-hand side. Then we have a second part with potential function, and then we have a with nonlinear function present, nonlinear term presented. So this psi function is a C function, is given to us basically, and we consider the Cauchy problem in the Sobolev space with S greater than real, which is just an algebra. It's algebra. That's why we can do it. And so now we have, we denote by C the complete subspace of CL, and we assume that t greater than 1 and supremum of function f, like this space is a set of all functions such that the support of these functions is in this set with x outside of this like set, like RID. R was the constant that was related to Schwarzschild radius. And so, and G, this operator, transfers this set to this set continuously. And we consider mapping. So we take a S, which we consider such operator, which acts as follows. So any function psi is given like this. And then this psi ID is, we already know it belongs to the space we are looking for the solution for. Yeah, we look for solution in that space. So this function psi we can generate using the initial data given. And we know the already estimates this, this norm can be estimated via the norm of initial functions. And for this S operator, we prove that this S operator X is actually contraction. And that's why we can apply the Banach-Fix theorem for this operator S. So we, first of all, we prove that this S is into, so any psi will be transferred to the, will stay in the space. And also we prove that the S is contraction. And with some, so we prove that with some gamma less than this estimate is given with used before, and support of the solution is in this space, which means that S psi also belong to the space. So if psi belong to the space, and then S psi is also belong to the given space, moreover S is contraction, so we can use Banach-Fix theorem, which will complete proof, our proof of the theorem of global existence. Okay, the case of smaller mass is also involving a lot of technical detail, but can be like done similarly. And so I like to stop here and thank you very much for your attention and invitation.
Thank you very much, Professor Anahint. Thank you again for accepting our invitation and for giving this very interesting talk. I will ask the audience if they have any questions. You can write them in the chat or raise your hand if you have them. Okay, well, the audience think their questions, I would like to ask out of curiosity if you have or have heard over the asymptotic behavior of this solution, perhaps some scattering, perhaps when times is very large, the nonlinear term is not that relevant or something like that. I don't know if you know anything about that.
No, I am not sure. No, I don't know about that, but that may be interesting thing to think about. Thank you very much for very good question and comment. I will look for that.
Thank you very much,
Maybe
Professor
some
Anahint.
results. Yeah.
Any other question? Yes, Duan, please.
Okay, okay. Thank you very much, Professor Anahit. I have actually a question about it was, I think, slide 30. Something took my attention that actually 30, I think.
13, yeah, I cannot see the numbers. I'm sorry. Yeah, okay,
Mm.
now. Yeah, okay. Yes, Lipschitz continues. Yes. Mhm. This is the question?
No, not here in the page 30. 30.
1, 3?
30.
Oh, 30, 30. Oh, okay. Sorry. I didn't hear. Yeah, so
Sorry.
yes, please.
Latin American English. So sorry, Latin American English. So
Yeah, this is
something
always problem, I know.
something took my attention because your model actually is very complex to my understanding, right? Because you have second derivatives in time, you have this term AHDF, which is
Yes.
an operator and so on. But that takes my attention is that you have an explicit solution for your model, right? I just wanted to
Yes,
have
this is very
maybe
interesting. Yes.
intuition about how you got this kind of expression.
Oh, yeah, this
It's
is a long
complex.
story. That is exactly the Lagrangian integral transform method I mentioned before. That was done in one of his papers many years ago. But then that approach actually helps us. Basically, you see, you use just the solution V, yeah, which is just the regular solution of Cauchy problem. And then using this approach, this is exactly, you have to look at his papers. This approach gives us really good representation of the solutions. So of course, there is these kernels are complicated, but they actually exactly given to you because you have this hypergeometric function inside. So that is really very powerful tool that was introduced by Yagjian. And that works in several occasions for several equations.
Thank you
Of
very
course,
much.
the kernels will be different, of course.
Right, very interesting. And maybe connected with the question of Manuel, right? About the maybe behavior of the solution. Could you please remind me, at the end, you have probably the conditions for your initial, so okay, so an hypothesis for your initial conditions, but what is the degree of regularity of your solution in Soulep spaces?
So we have a s greater than 3/2. Yes, we have
Uh-huh.
this condition. And also we have a small, like in our theorem, we assume that small solutions, norm is small.
Right.
Yeah,
Oh,
here,
okay.
sufficiently small in Sobolev space with s greater than 3/2.
Okay. And just last question, because of course was very interesting, very inspiring talk. This quantity M is the one that, because of this quantity, you have to divide your analysis, right? Between a small mass, the critical mass, and large one,
Yes,
right? This
because
quantity.
it changed the different properties of kernels and so on. Yes, because this quantity.
Okay, thank you very much. Thank you very much
Okay.
for it.
Okay. Thank you very much for invitation. I'm sorry that I am in not good setting now, but looks like it will look good because I'm inside of hospital.
No problem, Professor. Thank
You
you very
can
much.
see the hospitals in the US, how they look like. And they have a business area, and so you can do something.
Thank
And
you
I
very
was
much,
lucky
Professor
nobody
Anahit.
came. Okay,
Thank
thank
you
you
very
very
much.
much, and have a nice day. Rest, enjoy the rest of conference, and I will join tomorrow.
Thank you very much. Have a nice day.
Thank you very much. Bye. Bye.
Bye.
Okay, thank you. So I think we have with us our next speaker, Rakesh, Professor Rakesh Palmar, right? Professor Rakesh, I think you can unmute yourself.
Hello,
Hello.
Professor Duran.
Yes, Professor Rakesh
Can you hear me, sir?
Kumar. Yes. If you want to activate your camera, it's okay, and if you feel comfortable, and also maybe we can try to share your the presentation. Maybe you can try.
Here midnight is there in India. So it is around
Okay.
12:30. It is in India, it is 12:30 midnight now.
Wow, it's we cover all the possibles
Uh,
periods of the day, right? So now very early in the morning in India. So maybe you can try to share your screen.
yes, Professor.
Just for your information, you have already like 45 minutes for your presentation. Please feel free to use the time.
Okay, Professor.
Please.
Can you, I share my screen. Can you see the screen, sir?
I can see the screen. I think if you want, you can put in full screen mode. Full screen mode is okay for you.
I think it is full screen only, Professor.
So maybe you can use Control L. Control L.
Control L.
Control L. Otherwise, it's okay like that. I mean, or at the bottom of your computer, there are some signals, some arrows there. I think in the right hand side at the bottom.
Right hand side in the bottom. Yes, here it is there, sir.
Four arrows that indicates full mode, I think is that.
No, it is not here. I think it is.
Okay. In any case, I think it's very visible. Your presentation is visible. Okay, so
it is. I cannot change this setting.
don't worry. It's
it is
okay.
It's okay, no?
Yes, maybe let's try to move your slide. You can try to move your slide. Okay, so very good. So, see, it's working well.
It's working, but screen I cannot. I tried, but it cannot be screen full.
It's okay. You can pass. You can pass your slide very well. So,
shall I start?
Maybe we can wait 1 minute.
1 minute.
1 minute more, 2 minutes.
Yes, Professor.
1 minute, maybe. So thank you very much indeed for your interest in our conference. Right?
Thank you very much for your invitation also. I think I earlier 2-3 before years also I joined this conference. I am regularly you're sending the emails to me also. So sometimes in the conference that I am joining, I think pseudo some differential something conference was held earlier also. And then Michael Rujansky was there.
Yes.
At that time also I was there. I know that I have given one talk also in that conference. Michael Rujansky came in India. I met him in India in Jaipur city. He came in 2016.
2016. Yes, I did hear about that. Yes. Yes, indeed. Actually, I did join the research group of Professor Michael Ruchansky several years ago because I did my PhD thesis under his supervision. And later here in Ghent, here in Belgium, we start working very actively in Latin America after the pandemic time with this community, ICMAM Latin America, that actually now is somehow popular in our community because we have several activities, several initiatives, we organize several conferences. Initially, that was very focused on analysis and partial differential equations, but later we joined experts in different ideas and now extrapolate to all the areas in mathematics. So has been very active community.
I met him, Michael Rujansky, I met in Rajasthan. He came in Rajasthan in India, 2016.
Right.
And in the Facebook also, he's my in the Facebook friend also. So this conference,
Yeah.
no, previous conference, he only informed me.
Right. Right. Actually, there was a conference in London, 2016, in London, of analysis in developing countries that was organized by Michael Ruchansky and by Julio Delgado. And actually, the name of the conference was analysis in developing countries, I think. And then we took inspiration from that activity to continue a little bit, but this time supported by ISAAC and ICMAM. But ISAAC, this is International Society for Analysis, Applications, and Computation. So, but all this, of course, feels very inspired by the activities that were started by Julio Delgado and Michael Ruchansky from that time. When Professor Ruchansky was professor in Imperial College in London.
Okay. 10 years before visiting you.
Yeah, it's 10 years. Time goes very fast, right?
Very fast.
10 years, it's incredible. I remember I was very young that time. Okay, I think maybe we can start. So it's for me a great pleasure to introduce our next speaker, Professor Rakesh Kumar Parmar from the Department of Mathematics at the Ramanujan School of Mathematical Science in India. So Professor Parmar will talk about on generalized extended hypergeometric type higher transcendental functions. So please, Professor Parmar, the time is yours. Thank you.
Thank you, Professor Duran. First, I will thank you to invite me in this conference. I'm very thankful to this, you. And my title of talk is on generalized extended hypergeometric type higher transcendental function. So, thanks to organizing committee, other members also. So this is the joint work with my friend, colleague, Professor Tibor Kepogani from University of Rijeka, and Junseng Choi, Donggong University, Republic of Korea, and then Dragan Janko Masirevic, she is from University of Osijek. So the 2-3 papers combined research work is there. So outlines for this presentation, I will start from the gamma function, beta function, then Pockenberg symbol identities, Gauss hypergeometric function, confluent hypergeometric function, generalized hypergeometric function, and then I will go for the hypergeometric function of the 2 variables. Later 3 variables I will explain, and then multiple variables are also there. After that, certain PA or PQ extended type of special functions are there. And then I will show the generalizations by using this P and PQ extended special functions to the another higher transcendental functions are there, like Bessel function, modified Bessel functions, true functions are there. So starting from the factorial function, we know that factorial n is a n product of n natural numbers. Product of n is a positive integer or product of n natural numbers we are saying. And this notation, this symbol we are using, this was first introduced by French mathematician Christian Kramp in 1808. Later, another notation was there. this notation, and this was given by Thomas Jarrett in 1857. In 1771, Euler given the notation this, and later he used another symbol for this factorial. But nowadays it is common factorial notation we are using this, which is given by the Christian Krem. Now, one of the simplest but very important special function is the gamma function, whose properties is the prerequisite for the study of many other other fields, including calculus, analysis, special function, particularly in the theory of hypergeometric function. This gamma function was first appeared to extend the factorial n for the non-integer value in 1729 by Leonhard Euler. He was a Swiss mathematician from the St. Petersburg. In a correspondence to the Christian Goldbach, he was a German mathematician in the Moscow, along with Daniel Bernoulli. So Daniel Bernoulli and Christian Goldbach, they were solving a problem related to the triangular number. So in that, another one question arises: what will be the value of the factorial n if n is a real number greater than 0? Then what will be the value of this? Since factorial n is a product of n number, so like that they are thinking that if n is a half or some factorial, real number of like that it is there, then what will happen? So this they posed this problem to the Euler in 1729. Christian Goldbach and Daniel Bernoulli, they were working on a problem of triangular number like Tn equal to 1 plus 2 plus 3 plus n. We can see that this sum we can write in as a Tn is equal to n plus 1 by 2. So this formula can be interpreted for the non-integer value also. Then they were thinking that whether any expression is there, 1, 2, 3 product of n natural number, like this sum they are interpreting like this, one algebraic formula is there. So whether any sum is there and what is the value of n when non-integral is there. So they can't find this problem. So they posed this problem to Euler. In 1729, Euler proved that there is a no finite number of algebraic terms available for the factorial n. Here the algebraic sum is available, but for this, no algebraic sum is available for this factorial n. So the problem of giving factorial x a useful meaning when x is any positive real number, which was solved by in 1729 by Leonhard Euler, and who defined the following integral in 0 to 1 minus log t power x dt. Nowadays we are calling Euler's gamma function or Eulerian integral function. This integral, by making simple transformation x equal to e to the power minus t, and this will convert into another form which usually we are writing in this form. Now we are using this integral in this form. Gamma z is equal to 0 to infinity e power minus t, t to power z minus 1 dt, where real part of z greater than is equal to 0. This integral he given by taking Euler's solve this integral by using this integral by parts and then substituting here e equal to f by g and solved by the hospital rule and using the limit g tends to n, he got this integral representation. Now this notation gamma z, at that time this notation was not there. So this gamma z is due to the French mathematician E.M. Legendre in 1809. Some properties of the gamma functions are there, like recursion relation, or we say functional formula is there. Gamma z plus 1 is equal to z gamma z. Euler's reflection formula, gamma z into gamma 1 minus z is equal to pi upon sine pi z. Legendary duplication, well-known duplication formula, Gauss's multiplication formula is there, and various other properties are also there. Gamma function has a simple pole set z equal to minus n, where n is equal to 0, 1, 2, 3. Means gamma function is not defined in the negative values of the negative integers in the left half plane. And also gamma, interesting one point is that gamma z never takes value 0. So gamma z is never takes value 0. So it means reciprocal of the gamma is possible. So 1 upon gamma function, 1 upon gamma z exists. Here we can see the graph of the gamma function, that this is the reciprocal of the gamma function graph, and this is the the graph of the gamma function, real part of x greater than. Also, we are saying that gamma function is not defined with the negative integers also. But in the interval right half plane -1 to 0 or -2 to -1, -3 to -2, gamma function exists. And gamma for definition is there and graph is also exists. Now next is beta function. So the Eulerian integral of the first kind, beta xy of two complex variable x and y is defined by the Leonard Euler only in the 1730. And it is given by the integral representation 0 to 1 t power x minus 1 1 minus t y minus 1 dt, where real part of x and y greater than 0. This beta integral is closely related to the gamma function. So we can write beta function equal to gamma x gamma y upon gamma x plus y, where real part of x, real part of y greater than equal to 0. Also, the relation of beta integral in terms of gamma function was given by Euler in 1772. The beta function satisfies the symmetric property, means if we interchange x and y, so beta yx and beta xy value is the same only. The name beta function was introduced for the first time by the Jacques Binet in 1839. A.M. Legendre named beta function as Euler's integral of the first kind, and for the gamma function, Euler integral of the second kind. Since gamma function was introduced in 1729 and beta function was introduced in 1730, but Legendre given Euler's integral of the first kind beta, because while solving the integral representation, by finding the integral representation of the gamma function, he used integral of type beta function. Here we can see this type of beta function like that he used. So he given the name integral representation of first kind and second kind. Now next is Pochamber symbol. So the Pochamber symbol lambda n or rising factorial or shifting factorial, we are saying, is a generalization of factorial n only, having product of n factors beginning with any complex number lambda and increasing by steps of unity. Includes the special case if we put lambda equal to 1, so 1n equal to factorial n. So we are saying that it is a generalization of a factorial n, and it is defined by lambda n equal to lambda plus 1, like that, product of n factors, lambda plus n minus 1. This lambda function, this Pochamber symbol has a close association with the gamma function, and we can write the relation Pochamber of lambda n equal to gamma lambda plus n upon gamma lambda. Here in this Pochamber symbol, we are using this notation. So before that, in 1880, Apple given another symbol that is known as Apple symbol, and here it is written as bracket lambda n. Another symbol was given by Pochamber. No, nowadays we are using this symbol. It is given by Leo August Pochamber in 1890. Some Pochamber identities are there. If we put lambda equal to 1, 1n equal to factorial n. Similarly, like in the gamma function, duplication formula is there, addition formula is there, reflection formula is there, multiplication formula. So Pochamber symbol also is, since it is connected, it is related to the gamma function. So like that, Pochamber symbol also having some identities. Now the Gauss hypergeometry in this series of the form 1 plus AB upon CZ, AA plus 1, BB plus 1 upon CC plus 1, Z square by factorial and so on. Or in the summation form, we can write summation n 0 to infinity AN BN upon Cn, Pochamber AN, Pochamber BN upon Pochamber Cn, Z power n upon factorial n. So here we have used the property of the Pochamber symbol, this A plus 1, like that it is there, AA plus n minus 1, like that it is there. So we use this as a Pochamber symbol and written in this summation form. This function is called Gauss's hypergeometric function. Here A, B, C are the complex parameter and Z is a complex variable. It is called a hypergeometric series. Parameter A, B, C may assume all complex values with the exception C not equal to 0, -1, -2. Otherwise, it will be not defined. Also, hypergeometric function is symmetric in the parameters A, B. We change A and B, the value for the hypergeometric function will be the same only. Here, the leading subscript 2, this 2, indicates the 2 Pochamber symbol appears in the numerator, and the final subscript 1. It indicates one Pokemon symbol in the denominator. If either A or B is 0 or a negative integer, then the series terminate after a finite number of term and we get the sum as a polynomial in Z. This hypergeometric series was first studied by Leonhard Euler, but the first systematic development was given by C.F. Gauss in 1812. He presented his memorial, announced his famous memorial, General Investigation of Infinite Series in the Paris International Conference of Mathematicians. C.F. Gauss proved that this hypergeometric function not only a Euler's hypergeometric series, but also but also as the solution of a second order differential equation. He proved that this is a solution of this second order differential equation. And this differential equation having three regular singular points 0, 1, and infinity. 0, 1, and infinity. The initial value for the 0 is 0 and 1 minus c. For the 1, initial value is 0, c minus a minus b, and for the infinity, a and b. So total 1, 2, 3, 4, 5, 6 initial values are there. So total 6 solution will be there. Later, 3 hypergeometric transformation formula were given by Euler and Pop. So it means this 3 transformation formula, if we apply in the all these 6 initial equations, so 6 3s are 18, already 6 are there. So 18 plus 6, total 24 solutions are there for this hypergeometric series, and it was given by Kummer only in 1836. So the word hypergeometric in Greek, hyper means above or over. First nomenclature by the John Wallis in his book Arithmetica Infotorium to describe the infinite series of this form. Now this hypergeometric get its names from the fact that when we put in the 2f1 a, b, c, z, a equal to 1 and c equal to b, this hypergeometric series reduces to the elementary geometric series. By using confluence principle, that is, if we replace into f1 z by a and taking limit a tends to infinity into f1 a, b, c, z, we will get confluent hypergeometric of this form m0 to infinity bn cn upon z upon factorial n. This series was given by Kummer only. So we, in the name of Kummer, we are saying Kummer's function, or we are saying Kummer's confluent hypergeometric function or confluent hypergeometric function. Now we know the ratio of Pockenberg symbols can be written in one transformation formula in terms of beta functions. So Bn Pockenberg, Cn Pockenberg we can write easily in terms of beta b plus n c minus b upon beta b c minus b. Now using this transformation formula in the Gauss hypergeometric function definition, confluent hypergeometric definition function, we can write that series in terms of beta function also, because here this why we are writing in the beta function. Later extended beta function definition we will use, and we will this functions can be generalized in the beta function also. This hypergeometric function integral was given by Euler, and it is represented here in equation number 9. Gamma 2f1 a b c z equal to gamma c upon gamma a gamma c minus a 0 to 1 t power a minus 1 1 minus t c minus a minus 1 1 minus z t power minus b dt. This integral was given by Euler only. A similar integral representation is for the confluent hypergeometric function. Now the generalized hypergeometric function with R numerator and S denominator parameters is defined by the series representation RFS. Here R means R Pockenberg symbol in the numerator and S means S Pockenberg symbol in the denominator. So we can write this is the generalized hypergeometric series. So if in this series, and these are the convergence condition for this hypergeometric series. This we can find the convergence conditions by the ratio test. Now in this hypergeometric series, if we put R equal to 2, S equal to 1, and R equal to 1 and S equal to 1, we get the Gauss hypergeometric function 2f1 and confluent hypergeometric function 1f1 respectively. If we put in here R2 and S1, we will get 2f1. If we put 1, r equal to 1, s equal to 1, we will get confluent hypergeometric function. Again, if r equal to 3, s equal to 2, the function will reduce to 3f2, which is known as Clausian hypergeometric function in honor of Danish mathematician and astronomer Thomas Clausian. He given a very beautiful, established, beautiful hypergeometric identity. Means he proved that product of two hypergeometric function by taking specific value of c as a alpha plus beta plus half. The square of this hypergeometric function means product of this hypergeometric function will be reduced to a another function which can be written in terms of 3f2. So 3f2 was we that 3f2 was a name given by the this was developed by this identity by the Thomas Clausian only. So for the respect we are saying that this is a Clausian function. Now the some special cases of the hypergeometric functions are there. If we put particular value, the importance of this hypergeometric function is that almost all elementary functions, exponential, binomial, trigonometric, hyperbolic, logarithmic, are the special cases of this function. Suppose if we take value a equal to 1, b equal to 1, c equal to 2 and multiply by z, and then we will get log 1 plus z. Like that, so many special functions are there: tan inverse, sin inverse z, cos inverse z, sin z, cos z, exponentially, and binomial this expansion, and so many other special functions, other many higher transcendental functions are there. We can write in terms of hypergeometric function. Now, in the 2f1, if we take the value z equal to 1 or half or some other value half by putting b equal to 1 minus a, c equal to b, or c equal to 1 plus a minus b, z equal to minus half. So these all series will reduces to the product of some gamma function. This sum was given by Gauss summation formula. We are saying Gauss. This is given by Gauss only, Gauss second summation formula. And then this was given by Bailey summation formula, Bailey, W and Bailey, and this summation was given by Kumars. Now, generalization of the hypergeometric function, generalized hypergeometric function is known as Fox-Wright hypergeometric function. So the Fox hypergeometric function was given by Fox and Wright, and it is defined in the form of P psi q. Here we can see that the product of P product of the gamma function and denominator Q product of the gamma function. And this function is a generalization of the PFQ only. We can easily see that if in this function, if we put AJ and BJ, all AJ and BJ equal to 1, this function will reduces to this hypergeometric function generalized only by multiplicative sum term. Now, in 1880, Apple considered the product of two hypergeometric function, and he defined 4 type of hypergeometric function, which he named as if F1, then F2, F3, F4. F1 can be written first Apple's hypergeometric function can be written in terms of this summation form, and this again can be written in terms of single series involving 2f1 means this is the definition of the Apple's first hypergeometric function, and this in Apple function we can convert into single series involving 2f1. Similarly, this is the second Apple function, and same we can write in terms of 2f1 also. This is the third Apple function, and same we can write in terms of 2f1 also. This is the fourth Apple function, and same we can write in terms of 2f1 also. So these 4 functions of 2 variables are given by Apple only, and he named as a Apple function of hypergeometric function of 2 variables. Now, these all 2 variable hypergeometric functions were later unified and generalized by Kempe-de-Ferrit in the following form. This is the more generalized form of this Apple function: F1, F2, F3, F4, not only F1, F2, 3. So many confluent functions are there. That also special cases for this Kempe-de-Ferrit function. Now in 1882, Exton introduced the double hypergeometric function. He also given another type of double hypergeometric function, and is which double power series reads as in this form, where this symbol denotes the sequence of the parameter a1 to capital AA, and doubles bracket this stands for the product of Pockenberg symbols till A. In 1920, Humbert defined 7 confluent hypergeometric function of 2 variables from that 4 Apple function. So later in 1931, Jacob Horn, he defined 34 more hypergeometric series of 2 variables. The total 34 Horn function later were categorized into 14 complete hypergeometric function and 20 confluent hypergeometric function. This all functions, whatever I am saying here, this foreign function is well written in the monograph of the Srivastava and Manocha. Book name is Multiple Hypergeometric Function. One of the confluent hypergeometric function or the Horn's double hypergeometric function of 2 variable is given by H4, and it is written in summation form of this. In 1882, Exton studied the generalization of the Horn function and introduced 20 more triple hypergeometric functions, x1, x2, x3, like that, x20 functions are there. In that 21 of the 8th function I have written here, because maybe in further time will be there, I will show the generalization of this function. Now in P extended beta function, since in 1994, Chaudhary introduced definition of P extended beta integral. He given the integral representation of beta function beta x y. He introduced an extra parameter, and he defined a new integral representation for this definite 0 to 1 t power x minus 1 1 minus t y minus 1, and in the integrand he taken another factor e to the power minus p upon t minus 1 minus t. So here we can see, if I put p equal to 0, this exponential reduces to the 1, and we will get the original classical function of beta function. So he defined this generalization and named as a p extended beta function. He studied, they together, Chaudhary and their other colleagues, they studied various properties and obtained certain connections with the McDonald, error, and Whittaker function. Further, more interesting properties and connections with the higher tangential functions are investigated by Miller only. Yet already I told that in the obviously since case, p equal to 0, it reduces to the classical beta function. So these two papers are there. In that, he defined the extended beta function. In 2004, Chaudhary again replaced this beta function by p extended beta function. Means in that hypergeometric function, while before the slide, I saw that hypergeometric 2f1 can be written in terms of beta function. So that beta function he replaced by the extended beta function, and he named this whole series as a p extended Gaussian hypergeometric function. Similarly, p extended Commerce confluent hypergeometric function also he defined. They investigated various properties including differentiation formula, Mellin transformation formula, other transformation formulas are there, recurrence relation summation formula, asymptotic formula, and certain interesting connection with some known special functions like McDonald functions. Also they given connections with the Whittaker function, also they given. Later, Choi introduced two parametric extension of beta function, is this beta px. Since Chaudhary introduced only one parameter, so Choi introduced two parameter pq extended beta function. He defined beta x y pq equal to 0 to 1, t power x minus 1, 1 minus t, y minus 1, exponentially power minus p upon t minus q upon 1 minus t. Here we can see if p equal to q, this will reduce to the Chaudhary hypergeometric beta function. This Chaudhary hypergeometric beta function. And if we put p equal to 0 equal to q equal to 0, this will reduce to the classical beta function. So later in that paper, he defined Mellin transformation also. He find the Mellin transform of this function, and it is representation given by this product of the gamma function. Here you can see this is the beta function extended, and but Mellin transformation comes in the product of classical gamma functions only. Now, in that paper, Chaudhary given 4-5 integral representations of this beta function, extended beta function. Here we have given the representation integral 1. Here in another integral representation 2 of this extended beta function. Here extended beta function, integral representation of third one, and this is the fourth integral representation of this extended beta function. Also, they obtained some functional relation. In that functional relations, they given this functional relation, another summation formula for this beta function, summation formula for beta function again in the another form. So these two summation formulas and functional relations is given by the Choi and et al. Later connection with this Legori polynomial. So this beta function, if we replace y by 1 minus y, and if we see this can be written in terms of summation form, where here one L is defined by Legori polynomial, and it is generating function, it is the Legori polynomial generating is given by this only. I think in this something is missing here. Here Legori polynomial will be there, and it is term missing. Also, the connection with the measure G function is also given by this. Means this beta function of two parametric beta function, we can write in terms of G function, measure G function of two variable. And one more thing, this extended beta function of two variable, we can write in terms of apple function of two variable. Second apple function also. Again, if we replace y by minus alpha, x by alpha, and we see this having a connection with the McDonald function k, or modified Bessel function of the third kind also we see. This another this beta function we have find here Legori polynomial connection with the and the Whittaker function. So this is the Legori polynomial and Vita function. This is the connection between the Legori polynomial Vita function. We can write this beta function in terms of these functions also. Later, Choi introduced two parametric extension of this extended hypergeometric function. Instead of parameter p, he take parameter pq, and he defined pq extended Gauss hypergeometric function and pq extended pq extended Kummer's confident hypergeometric function. Various properties, integral representation, differentiation formula, Mellin transformation formula, recurrence relations, summation formulas, and certain interesting connection with some known special functions are also established. Bessel and modified Bessel. These Bessel functions are named for German astronomer Friedrich Wilhelm Bessel during an investigation of solutions of one of Kepler's equation of planetary motion, who was first achieved fame by computing the orbit of Halley comet. However, Daniel Bernoulli is generally credited with the being the first to introduce this concept of Bessel function in 1732, who was studying the oscillatory behavior of a hanging chain. The series representation of Bessel function of first kind of order nu is given by this, and this is the series representation of the modified Bessel function of the first kind. This both series representation can be written in terms of hypergeometric function also. So this hypergeometric representation of Bessel function it is given by, and this is the modified Bessel function hypergeometric connection. Now, by making use of this straightforward identity, we are already using. So we replace this identity. We can write this Bessel function, means we can write this series in terms of beta function also. Here we written this beta function in this series form. Now, in the summation, beta function is there. So we replace this beta by extended beta function, PQ extended beta function. So that our new function will be there, that is known as PQ extended Bessel function, PQ extended modified Bessel function. So here, in terms of extended beta function of two-way parametric extension of beta function, we have defined PQ extended Bessel function of first kind and PQ extended modified Bessel function of second kind. Later, by using integral representation of beta function, PQ extended beta function, integral representation of beta function, if we use here and if we simplify this summation and interchanging integral, we will get two integral representation of Bessel function and modified Bessel function here. The interesting thing is that we can see here if P and EQ equal to 0, we will get the classical integral representation of the Bessel function. So these are the two bounding inequalities are also given in that paper. Later, Mellin transformation of this extended beta function and this extended PQ extended Bessel function and PQ extended modified Bessel function. These are the Mellin transform of this function. You can see here, this is the function including two parameter PQ, but final result is classical results only. Means this function is 1F2 means it's in the classical form. No PQ is there here. So Mellin transform of same modified Bessel function is given by this form. After systematic examination of this PQ extended Bessel function and modified Bessel, we can naturally switch to the other Bessel type of functions like Struve function and modified Struve function. Here, the Struve function definition in the series form is given by this, and the modified Struve function definition is given by this only. Now, like similar in the beta function, in the PQ extended Bessel function, we replaced that beta function by the extended beta function. So similarly, we will convert this both function in the form of beta function and we replace that beta by beta PQ. So this is the new form of series form of PQ extended Struve function and PQ extended modified Struve function. So again, if I take integral representation of this beta function and I use here and changing the order of integration and summation, we will get another new two integral representation. In this integral representation, if we put P equal to Q equal to 0, we will get the classical integral representations. In the same analogous Barrick's, Arpad Barrick's, he defined another type of Bessel function as known as generalized Bessel function. In that Bessel function, he defined it includes four cases. One is one is Bessel function, second is modified Bessel function, third is spherical Bessel function, and fourth is modified spherical Bessel function. So like that, what we done here, we extended this beta function, replaced that beta function by the PQ extended beta function, so that now our new functions will be constructed that is known as PQ extended generalized Bessel function. So same, if we put here C and here small b, particular values means if we put b equal to c equal to 1, we will get PQ extended Bessel function. If we put b equal to 1, c equal to minus 1, we will get PQ extended modified Bessel function. If we put p equal to 2, c equal to 1, we will get PQ extended spherical Bessel function. And if we put b equal to 2, c equal to minus 1, we will get PQ extended modified spherical Bessel function. Now, two integral representations for these functions are there. If we replace beta integral here and changing the order of we will get this integral representation. Here in this another integral, this we can obtain by this only if by we putting t equal to cos theta, we will get this integral representation. Another new family of the Bessel function is PQ extended Bessel-Struve function. So that is known as Bessel-Struve kernel function we are saying, and its notation is given by S nu only. Here S nu can be defined in terms of this series form. So here again we can write this function in terms of beta function also. After converting this beta function, we will replace this beta function by the PQ extended beta function only. So we will get PQ extended Bessel-Struve kernel function. Now if we write here integral representation of PQ extended beta function and then later simplifying, we will get integral representation of the PQ extended Struve function. Now we will move to the another type of higher transcendental function that we say PQ extended elliptic integral. Before that, we will start some elementary things of the elliptic integral. The elliptic integral, if the integral of this form, integral of this form r x comma root px, where rx is the rational function of x and px is a polynomial of third or fourth degree, and it can be written in like that. Here one condition is there that both a0 a1 cannot not both equal to 0, means a0 and a1 both simultaneously cannot be 0. And if we put this px equal to 0, whatever the roots come, the condition is no repeated roots will be there. If this condition is fulfilled, one condition is this, second is this. If this condition fulfills, it means the integral of this form always called a elliptic integral. This elliptical integral cannot in general expressed in terms of elementary function. Integral of this type were encountered very early history of the calculus in finding the length of the arc of ellipse, and hence they came to be called elliptic integrals. They also arise in connection to the arc length of hyperbola, Bernoulli lemniscate, the surface area of ellipsoid, motion in pendulum, and many other problems in the applied and pure mathematics. Now, the classical legendary complete elliptic integral is defined by kk and ek of the first and second kind. Here we can see this is the complete elliptic integral of the first kind, kk, either 0 to pi by 2 d theta upon under root 1 minus k square sin square theta, or we can write if we replace sin square theta is equal to t square, like that. If we simplify this, so we can get another integral representing 0 to 1 dt upon under root 1 minus t square 1 minus k square t square. And another second type of elliptic integral is notation is given by ek, and same like that we can write this elliptic and integral kk like this integral, and this we can write in this form. This integral form, if we simplify, this can be reduced in terms of 2f1. So it means elliptic integral of first kind can be written in terms of 2f1 also. Similarly, elliptic integral of second kind, this is first kind, second kind also we can put in terms of 2f1 also. These elliptic integrals have a remarkably large number of applications in the theory of Cauchy conformal mapping, physics, engineering, mean value theory, number theory, geometry, geodesics, radiation physics problem, nuclear technology, studies of crystallographic minimal surface, the theory of scattering, and so many areas are there in that they are useful, this integral. The remarkable large number of general families of elliptic and generalization of this classical, so many are in so many references are there, they have already studied. Here we are studying different type of generalization. Another Bushell given introduced another integral form of which he called a generalized elliptic integral h k gamma. So here what he done, he this both integral represented this and this, he combined and defined one new integral representation of this form, where if we put gamma equal to 0, if we put gamma equal to 1, we will get elliptic integral of first kind and elliptic integral of second kind. So similarly, like this elliptic integral, generalized elliptic integral, we can again define the another extension of PQ extended complete elliptic integral of this kind. Here we can see if we put p equal to 0, q equal to 0, again we will get classical integral representation of generalized elliptic integral. Now the special case reduces this PQ, means this integral representation. So many special cases are there. So if we put gamma equal to 0, if we put gamma equal to 1, we will get PQ extended complete elliptic integral type integral of first kind. And another, if we put another PQ elliptic integral of second kind known as EPQ. So these two integral special cases of that integral representation is. Later, PQ extended hypergeometric function representation. It can be written in terms of hypergeometric also in terms of PQ extended hypergeometric function. Similarly, this KPQ also can be written in terms of PQ extended hypergeometric function. So PQ extended hypergeometric function we can write. Third kind also, second kind of elliptic integral also we can write. So all these elliptic integrals PQ extended we can write in terms of PQ extended Gaussian hypergeometric function also. Similarly, these also can be written in terms of first Apple function. All this integral we can write in terms of first Apple also, PQ extended Apple also. Now these are the Mellin transform of this function, and we can see here this is the PQ extended elliptic integral, but result we are getting in terms of 2f1 means we are getting the result in terms of classical only. And this is the Mellin transform of this function. And this is, if we put gamma equal to 0 and gamma equal to 1, we will get special cases of that as a elliptic integral of first kind and second kind. Now, in this Mellin transform, if we see, if we put k s equal to 1, r equal to 1 and s equal to 1, and we can see that this beta function, this integral, double integral representation having hypergeometric connection, and this also double integral representation having connection with the elliptical integral of third kind. It is called elliptical integral of third. These are similarly results for the elliptic integral of second one, E. Now, this elliptic integral can be written having relation with the Legori polynomial, and here it is written for the h also. If we put gamma equal to 0 and 1, we will get the same relation for the k and E also. Now the special parametric value. Since in the beta function definition, like that elliptic integral definition is there. So if we put specific values 0, 1, here 0, 1, or in the k and ek, we can see that this or kpk can be reduced in terms of beta function beta pq half and half. Now we know the relation of this pq function. Before some slides, we seen that this bpq can be written in terms of g function of two variables. So all these functions can be written in terms of g function. Since this is the relation, beta function having the connection with the g function of two variables. So now what we are doing, we are using here this identity means delta and sigma half half. And if we are putting here, we will get connections with the g function. All these elliptic integrals having connection with the g function. So this is the another elliptic function having connection with the, this is another elliptic function having connection with the g function. The following, these are the derivative formulas for the this elliptic integrals, and these are the also again derivative formula for these two elliptic type of integral. These are the integral forms of the elliptic integral of first and second kind, and these we have studied this elliptic integral, some log convexity properties and Turan type integral. Here we can see this elliptic integral with respect to gamma is log convex, and with respect to p also this function is a log convex, and with respect to q also it is a log convex function. Now if we put all these special cases gamma equal to 0 and 1, we will get this another new results from this case for the elliptic integral of first and second kind. Later, these are the Turan type inequalities we can obtain by the log convexity property. Again, we are putting gamma equal to 0 and 1, we are getting some few more elliptic, few more Turan type inequalities. So similarly, we can see here another type of generalized complete elliptic integral is here, that is known as Ka, where it can be written, it is defined by in terms of 2f1. So like that, it is Ka. So we again generalize this Ka as a Kap Here we will replace 2f1 by extended hypergeometric function. So we replace this kap by p, means we replaced fp by 2f1 by fp. So this is the new p generalized elliptic integral. These are the integral representation of this new p, k and e. E means here epsilon we are writing, notations we have used. And these two functional bounds are there. This we obtained by the integral representation of these two functions. And now these are some other properties of this there. And this having connection with this hypergeometry. So I will end my this talk. These are the some reference. Thank you very much for that.
Okay. Professor Rakesh Kumar Parmar, thank you very much for your very nice presentation. I just shared with our team that was very well documented presentation. I see very nice references. Are there questions for Professor Rakesh Kumar? So I think that people are happy with your presentation. I just has a question, has a curiosity, right? Of course I am not an specialist in special functions, but let's say for the harmonic oscillator, right? One notes eigenvalues, right? Are Hermite functions for Laguerre operator. Then one has also eigenvalues, right? That are Laguerre functions, but there are other kind of than one called harmonic oscillators and so on. My question is if, according to your perspective of research, if you know operators where these kind of special functions could arise as eigen functions.
Actually, Professor, you are asking about some operators.
Right.
So operators are there. So this is, right now I don't know about these operators from where it arises, but this I am particularly filled my field is special function only. So I'm working on the special function.
Special functions, right? And maybe for information for the attendees, if maybe you can share a couple of open problems in your topic, in your field.
Okay.
Maybe could you please mention some open problems that you have in your in your topic?
I am particularly doing in the work of that like special function as Bessel function, Mittag-Leffler functions are there, and right function is there, gamma function, and some other extended beta functions are there. Some hypergeometric function of one variable, two variables. These types of special functions I am continuing. Bessel modified Bessel function, McDonald function, Newman functions are there, H function, G function. So my particular field is this special function of this types of problem. So higher transcendental function, yes.
Okay. Thank you very much. Thank you very much. I remember a couple of years ago we used explicit with some colleagues we used explicit asymptotic behavior of special
Yes.
functions, in particular Hermite functions for the boundedness of
Yes.
the harmonic oscillator in LP space. So maybe there should be some bridge, right? Between our topics. Thank you very much.
Thank you, Professor.
Thank you. Okay, I think.
Can I leave the meeting?
Yes, you can stop sharing. I think. We have a comment from Selma. Selma from my colleague Selma from Tunisia, I think, right? Just let me see. Maybe Selma has a comment, right? Selma, can you try to unmute yourself? because I think Selma is actually a woman mathematician from Tunisia. I think she has a comment. Okay, she says in the chat, she says that the operator should arise from differential
The
equations.
differential equation satisfy this generalized special. Okay.
Okay. If Selma wants to share,
She given the answer of your question. The operator should arise from the differential equation satisfy the generalized special.
Okay, very good. Thank you very much. Of course, very interesting. So thank you. I think then we have with us the next speaker, our last speaker, Professor Dharmendra. Are you there? I think he's our last speaker today. Professor Dharmendra Kumar, could you please try to unmute yourself? And if you want to activate your camera.
Yes, so.
Very good. So. Okay, so please try also to share your presentation.
Yes, sir. Sure.
Thank you,
Hi.
Dharmendra. Thank you. Please try to share your presentation. You can have a short talk, long talk, how you prefer. Okay. We see your screen, but not your presentation yet.
Is it visual? Yes, hello.
I saw that you are sharing your screen, but we cannot see your presentation.
Oh.
Or I at least I can't.
Oh. I will try to share my.
Maybe you can stop sharing and you can try to open the PDF. So open the PDF. Maybe not opening it in your navigator, but has a PDF in your desktop. I think it should work.
No, I will try to open my PDF, but.
Okay.
So. Is it visual? My.
No, probably you have to share your screen again.
Oh.
So we can see your screen and we can see your navigator that you have Masainet open, Overleaf, Google Translate, but not your presentation.
When we open disable motion that's
Is your presentation in PDF?
yes. My presentation PDF.
We can see your overleaf. Maybe you can generate
Oh.
we can see overleaf.
Yes, this is my overlay. Is it visible?
Is it visible?
But it is in the PDF overlay, I think.
You want to present in the overleaf?
I will try to share my PDF, but I
Okay.
have not.
Don't worry. We can try. Maybe if you want, you
Yes,
can try
yes.
to generate the PDF and see. You can generate the PDF. Maybe try to download your PDF if you want. Very good. So
Is it visible?
for some reason, we cannot see your
My
PDF
PDF.
presentation.
Yes.
Or maybe because I'm trying to see what happened. Maybe try to open your PDF in the navigator to see if you can present later another window, right?
Yes.
Maybe open your presentation. You can open your presentation in a new tab. Can you hear me, Dharmendra? Dharmendra, I think you are mute. You are mute, I think.
The PDFs I want to share this PDF also. Yes. Is it visible or not?
It's not visible. It's not
My
visible.
PDF.
Your PDF is not visible. What do you think about sending us your presentation? We can present it for you. Maybe you can send us your presentation by email.
Yes,
We can present it for you. Okay. It's normal. We understand that sometimes something happened with Zoom and maybe one cannot present, but just maybe stop sharing, send us your presentation by email, and then we can share for you.
Is it visible?
No, it's not visible. Maybe send us your presentation by email. Then we can.
Now is it?
Sorry, no, we cannot see your presentation. You stop sharing your screen.
Okay. I think I have to send my presentation in email. Please check your email.
Okay.
Mr. Upukyu.
Okay, thank you very much. So I think we got your presentation.
Yes.
We got your presentation, so just give me 1 minute. Okay, I understand what is happening. Your presentation is PowerPoint?
No, Pele-Wiener theorem for the Bessel-Wavelet transform.
Right, but it's a PowerPoint file or it is a PDF?
PDF file.
It's strange. For some reason,
MKC0560 is my email and my name is Dharmendra Kumar.
okay. I think we got it. I got it. So just please give me 1 minute. I will share your
Yes.
presentation. You can indicate me, you can indicate me when you want that I pass the slides, and then I will follow, okay? So, is visible your presentation?
Yes.
Is it okay like this?
Yes.
Can you see well it?
Yes.
Please indicate me, and then I will pass the presentation for you, okay?
Okay.
Okay, just please allow me just make a short presentation of you for the attendees. It's my great pleasure to introduce our last speaker today, Professor Dharmendra Kumar from Banaras Hindu
Hindu
University.
University.
So he will talk about polynomial theorems for the Bessel wavelet transformation. So thank you very much for accepting our invitation, Professor Dharmendra. Please continue.
Okay. Thank you, Mr. Diwan, and thank you all of the participants which are connected at that time. Now, I am especially thanks to all the participants of this conferences, and I am thanks to Mr. Diwan to give me my chance to present my work. The title of my work is the Pele-Wiener theorem for the Bessel-Wavelet transformation. This article published in 2024 in the Journal of Integral Transform and Special Function, and this is the completed work of myself. This is the outline, introduction, Pele-Wiener theorem, and the Pele-Wiener theorem to generalize function spaces. This is the introduction part, and as we know, the Pele-Wiener theorem is one of the fundamental results in harmonic analysis. It describes the relation between the decay property of function and the support property of its Fourier transforms. It is, if we know how the function is decay, then the support property, that is the Fourier transformation of that function with support, where the support lie or not, or it is contained or outside the domain or in particular thank you. In particular, it characterization of function whose Fourier transform have compact support. Over the years, several mathematicians extended this theorem to other integral transform, in particular Pele-Wiener type result for Hankel transform were studied by Anderson in 1, 2, 3, Kenchev in 4 and 5, Pathak in 6, Howie and Javed in 7, Abriva in 8, Griffith in 9, and Jamanian in 10. I think these works establishes important result describing the growth, behavior, and analytic property of the Hankel transformation. Please, next. Oh, thank you. Further progress in this direction was made by several authors like Kiprion and Kulkyu in 11 established Pele-Wiener type result for the n-dimensional Fourier Hankel transformation. Betancourt, Linus, and Mendage in 12 proved the weighted LP version of the Pele-Wiener theorem for the Hankel transform. And in last, these results were motivated by earlier work of Genchev in 1314 and Genchev and Hang in 15. These contributions significantly expand the theory of Pele-Wiener type theorem for the Hankel related transform and Hankel type transformation. Please. Oh. This is the extension of generalized functions. In 1985, Columbia in 16 and 17 introduced a new framework of generalized functions. This theory allows multiplication of distributions and provide a powerful tool to study singular problems. Using this framework, Karunakaran Vijayan in 18 and Suragi in 19 extended the Pele-Wiener theorem to Columbia type generalized functions. Later, Betancourt and Mesa in 20 and 21. Oh, please. Oh, thank you. We studied the Hankel transformation in Columbia type generalized function spaces. Now, please next. Oh, sir. This is my motivation. I think the Bessel-Wavelet transform is closely related to Hankel transformation. In fact, the Bessel-Wavelet transform can be written in the term of Hankel transform. This necessarily raises the following question. If the Bessel-Wavelet transform can be expressed in terms of Hankel transform, can Pele-Wiener type theorem also establish for the Bessel-Wavelet transformation? Motivated by this question, we investigate Pele-Wiener type result of the Bessel-Wavelet transform. Please. Motivated by the works of Betancourt at 12, 20, and 21, we study the Bessel-Wavelet transformation. And in this work, we introduce a class of Columbia type generalized functions, study the Bessel-Wavelet transformation on these spaces, and lastly establishes Pele-Wiener theorem for the Bessel-Wavelet transform on the space generalized function spaces E square mu sigma and on the Columbia type generalized function spaces. Before presenting our main result, let us briefly recall some important definition and spaces. This is the first definition, is the Hankel transformation. I think all of you know the Hankel transformation is defined by this equation. If phi is any function, this is belong to in L1 space, then the Hankel transformation is this function is equal to integration 0 to infinity square root xy j mu xy phi of x ds. And if the Hankel transformation of that function is exists in L1 space, then the inverse Hankel transformation is defined as phi x equal to integration 0 to infinity square root xy j mu Hankel transformation of that function into dy. Where j mu denotes the Bessel function of first kind, please first kind of order mu greater than minus 1 by 2. Similarly, Hankel convolution of two functions is defined via this equation integration 0 to infinity phi of y tau x phi 2y dy, where tau x is the translation operator and defined as tau of x into phi equal to integration 0 to infinity phi of z d mu xy z dz, where d mu is a basic function of the Hankel transformation. Now we see the definition of Bessel-Wavelet transformation. For more information, you see the reference 22 and 23. The continuous Bessel-Wavelet transformation is defined as via this equation B psi f s comma a equal to integration 0 to infinity f of t tau of s psi of a t dt, where tau of s is a translation operator, psi of a is the basic function, and it can be also written as via this equation Bessel value transformation equal to a to power minus mu minus 1 by 2 integration 0 to infinity f of t psi of t by a comma s by a dt, where s is greater than or equal to 0, a is positive, and mu greater than or equal to minus 1 by 2. And we know the Hankel transformation and the Bessel value transformation is like I just same to each other for function, that is the Bessel value transformation can be written as expression of Hankel transformation via this equation. Bessel value transformation is equal to, if you see this function y power minus mu minus 1 by 2 s mu f y s mu psi y, then this is a actual Hankel transformation of this function, So this is a Hankel representation of Bessel value transformation, I think. Now we see the test function spaces definition. In order to study the Bessel value transformation and establish the Belle-Wiener theorem, we recall the test function space y mu d and b mu d and introduce the space of entire function E square mu c. The space b mu d first space for d positive and space b mu d consist of smooth complex valued function phi such that phi of theta equal to 0 for each theta greater than t, and the supremum of this quantity, that is modulus value of theta power minus 1 derivative whole की power k times derivative है, I think. Bracket theta power minus mu minus 1 by 2 phi of theta less than finite, that is this is finite, then this type of function contained in the b mu d. Similarly, we define the space y mu d of function phi is contained in y mu d if and only if z minus mu minus 1 by 2 phi of z is even entire function such that supremum of this quantity is finite, that is exponential minus d imaginary z and this imaginary z modulus value of z power 2k minus mu minus 1 by 2 phi of z is finite for each k belong to natural number. So this is a natural number. Please next. This is space which we defined for generalized function space. For sigma positive, the space E mu sigma square consists of complex valued smooth function phi such that this z1 z2 for minus mu minus 1 by 2 phi of z1 z2 is even entire function, and for each epsilon positive there exists a constant a epsilon positive such that this quantity, whole quantity, modulus value of this quantity less than a epsilon exponential sigma plus epsilon modulus value of z1 to z2 for all z1 and z2 belong to C cross C. Before the main Pele-Wiener theorem, we see some important lemma related to the Bessel value transform in earlier spaces, which we defined. This is the lemma 1.1, and this is a Bessel value transformation. For mu greater than or equal to minus 1 by 2, the Bessel value transformation is a continuous mapping from b mu d to y dash mu d dash. This is the dual space of y mu d, and it can be easily see that if f belong to this space and the psi is any function in this, then the Bessel value transform b psi belong to the dual space of this space. This is the lemma 1.1. Now we see the lemma 1.2, for mu greater than or equal to -1, the Bessel-Bellevue transformation is a continuous mapping from y mu d to y dash mu d. And this is a dual space of this, then the continuous Bessel-Bellevue transformation is continuous map from this space to this space. This means that if F belongs to the space y mu d, then its Bessel-Bellevue transformation belong to the dual of this space. Thus, the Bessel-Bellevue transformation preserves the structure of the test function spaces. This is the lemma 1.3. For each f non-zero belong to dual of y mu d and psi belong to b mu d, the inverse Bessel-Bellevue transformation exists and belong to the space this. Here d depends on the parameter s and a. Now we're combining lemma 1.1, 1.2, and 1.3. We see our main result, that is Pele-Wiener theorem for the Bessel-Bellevue transformation. This is the first theorem. If f belong to generalized function spaces E square mu sigma and psi belong to b mu d, and assume that if this quantity is finite, that is integration 0 to infinity double integration s a की power minus mu minus 1/2 modulus value of f of s dA finite, and this quantity is also finite, integration 0 to infinity s की power mu plus 1/2 Hankel transformation of f into Hankel transformation of psi dx is finite, then there is a continuous function s such that f can be represented as the Bessel-Bellevue transformation of this continuous function x, where x is contained in. This is the, please, next slide. Okay. This is my second theorem in series of the Pele-Wiener theorem for the Bessel-Bellevue transform. If f belong to E mu sigma square and psi belong to this, and if this quantity 0 to infinity f power minus mu minus 1/2 f of s ds finite, and also this quantity also finite, integration 0 to infinity s power mu plus 1/2 Hankel transformation of f and Hankel transformation of psi dx finite, then the Bessel-Bellevue transformation can be written as a new function. It is Bessel-Bellevue transformation of f equal to g of s comma where a, where the property of g of s, g function is g of s comma equal to 0 for each s greater than or equal to sigma, where sigma is C in the generalized function spaces. This is the theorem 2, and this is the weighted LP version. Please. Yes. This is the weighted LP version of Pele-Wiener theorem for the Bessel-Bellevue transformation. If alpha and beta greater than or equal to 1, psi belong to b mu d, with theta and neta be in H alpha beta and F be in E squares mu sigma, the generalized function, such that this quantity s power minus mu minus 1/2 f and f are in this space L alpha and neta. Assume also that neta power minus alpha by beta is integrable in the interval 0 to sigma plus delta for every delta positive, that there is C and M positive such that neta s greater than or equal to C for every s greater than M, and that theta s is positive almost everywhere s belong to interval sigma to infinity. Then the Bessel-Bellevue transformation is in this space, that is weighted L2 space, and weight is dA by A power 2 mu plus 1 cross L alpha comma theta I, which vanishes in sigma comma infinity interval, except at most in zero major set, that is the almost everywhere. This theorem is now we see the Coulomb type generalized function spaces, and in this section we extend the Pele-Wiener theorem for the Bessel-Wavelet transformation to the framework of Coulomb type generalized function spaces. The aim is to study the behavior of Bessel-Wavelet transform on tempered H-type generalized function and characterize its image via the Pele-Wiener theorem. Now we see the definition of some test function spaces. First is AQ mu R square. Let D be space of all infinitely continuous function with compact support. So for each Q belong to natural number, we define the space AQ mu as the set of function phi satisfying integration gamma 1, gamma 2 का product power mu plus 1 by 2 phi of gamma d gamma is a quantity alpha mu, and the integration of this quantity gamma 1 के power 2k1 plus mu plus 1 by 2 gamma 2 के power 2k2 plus mu plus 1 by 2 phi of gamma d gamma equal to 0. For k1 plus k2 varies between the interval 1 to q, and alpha u equal to 2 power mu and gamma function of mu plus 1. This is AQ mu space. Now we see next space H tau mu. Let's jive mu I cross I be the set of function as x from A1 mu. Cross I to C, which are smooth for each fixed Q, each fixed phi. Then this type of function is contained in jive mu, and the quotient space of this space jive mu and n mu tau is called the space of tempered H-type generalized function, and which is denoted by H tau mu I cross. This is a tempered H-type generalized function space. This next, yes, where n tau mu the space of subspace of this space that consists of all those function x having the following properties. For each k belong to natural number, there exists a p belong to natural number and a sequence gn in gamma such that for every n greater than or equal to p and the phi belong to a n mu, there are m and delta positive for which the modulus value of lambda 1 power minus 1 d lambda 1 whole power k1 and lambda 2 power minus 1 d lambda 2 whole power k2 lambda 1 lambda 2 whole power minus mu minus 1 by 2 x phi of epsilon is less than or equal to m 1 plus lambda 1 square whole power p 1 plus lambda 2 square whole power p epsilon gn minus p. Now we define the Bessel-Wavelet transform in this generalized function space. That is the tempered H-type space. Bessel-Wavelet transform. For f belong to this with representative R, the Bessel-Wavelet transformation is defined as this equation, where the Bessel-Wavelet transform of this representation is defined by this equation. Now we see the converging property of Bessel-Wavelet transform. Let f belong to this space A and mu and psi in beta mu D, then this quantity is convergent to 1 as epsilon tends to 0. This is the convergent property of the Bessel-Wavelet transformation. The proof, please, next slide. Okay. Now this is the Pele-Wiener theorem for tempered H-type spaces. Theorem 4. The Bessel-Wavelet transformation is a continuous linear mapping from H mu tau to tempered H mu tau space. This result establishes the well definition of the transform on tempered H-type generalized function spaces. In series, we see last theorem number 5 in Pele-Wiener theorem for the Bessel-Wavelet transformation in tempered H-type or Coulomb type space. For psi belong to beta mu, the Bessel-Wavelet transform is 1-to-1 from H mu tau C to tempered H-type spaces. Moreover, every element of this space can be represented as the Bessel-Wavelet transform of the some element of these spaces. This is the actual definition of the one function. Now, next slide. Yes, so the conclusion of this article is we establishes the Bessel-Wavelet transform on tempered H-type generalized functions. Continuity and linearity of the transform. Pele-Wiener type characterization in Coulomb setting. These results extend classical harmonic analysis result to the framework of the generalized function. This work is published in integral transformation in 2024. Now the next slide is, yes, this is my references. These are all the reference.
Okay.
Yes.
Okay. Professor Dharmendra Kumar, thank you very much for your very nice presentation. Just it was interesting to see that you published your results in this journal, right? Integral Transform and Special Functions.
Yes.
That actually is quite very well recognized for a journal for special functions, right? The special functions
Yes.
and in analysis. Okay, thank you very much. So, are there questions for Professor Kumar?
Yes.
Is there someone having questions for Professor Kumar? Remember that to ask some question, you can raise your hand.
Yes, sorry.
I think our attendees are very happy with your presentation. I think they don't have questions. Maybe I have a question
Yes.
related to. I think it was this. Sorry, I think this is this a slide, right? When you have this Bessel-Wavelet transform, right? That you take one function in this space, each mu tau, but then you take
Yes.
one representative, right? And then you find the Bessel-Wavelet transform in the representative, right? So
Yes, sir.
this doesn't depend on the representative, right? Is the point?
Yes.
Uh-huh.
Yes, yes.
Because this is an equivalent class, right? F is an element
Yes,
in
yes,
here.
yes. This is a via the equivalence class we defined the representation of this function, and the Bessel-Wavelet transformation is totally depend on the representation of this function.
Okay. Thank you very much. And maybe sorry to go to another question that I have from the very beginning when you define the Henkel transform, right?
Yes, yes, yes.
Okay, you have Henkel transform, and also you have an explicit formula for the inverse Henkel transform.
Yes, yes.
Because very interesting, because if you have some transformation and the Fourier inversion, but okay, sorry, it's not Fourier inversion, but inverse Hankel transform also, then maybe you can have a notion of pseudo-differential operator, right?
Yes.
Pseudo-differential operator, right? For Hankel transform. Maybe that's known in the literature. I don't know, because I am not a specialist in this topic, but very good. Maybe
Oh, thank you.
we can check if there are how much people have done in literature about pseudo-differential operator for the Hankel transform, right? Because if you can define pseudo-differential operators with this transformation, then it's natural to ask for classes of symbols, for boundedness properties, for those
Yes.
operators. That maybe here Manuel and Martinez and Federico Poco, they work in boundedness properties, in particular in boundedness properties of pseudo-differential operators and Fourier integral operators. So maybe other perspective to have one notion of this Hankel transform. Right? Thank you very much.
Oh,
Thank you very much. I think very good.
oh,
I think we don't have more. I think we don't have more questions from the attendees, but we were very happy with your presentation, Professor Kumar. Thank you.
thank you. Thank you. Thank you.
It's a pleasure to have you.
Oh.
So, maybe new notion of the differential operators, so people actually have studied this. Maybe in future we can try to see if there are some simple classes for it and boundedness properties of these operators, or if there is some motivation to analyze them. So, thank you. So thank you. This was the last talk of this of our conference today. So I really invite you tomorrow to join us in the plenary talk of Professor Jacqueline Godoy Mesquita, who actually is a woman mathematician very well recognized in the community, because she's president of the Latin American Community of Mathematicians, the Latin American Mathematical Union, and former president of the Brazilian Mathematical Society. So I really encourage you to join us in our program tomorrow. Thank you very much, and to everyone, and see you tomorrow. Thank you.